There is an almost paradoxical feeling that has accompanied humankind since the first time we looked up at the sky, the feeling of absolute freedom and invisible confinement. When we gaze into space, it seems that anything is possible. The stars are there, silent, scattered in every direction, suggesting an open, vast, and accessible universe. But just a slightly deeper look reveals an uncomfortable truth. We are not only on an isolated planet, but inside a cosmic prison. A prison without walls, yet with bars of invisible energy. A prison shaped by gravity, by physics, and by the limitations of matter itself. The solar system is, at the same time, a sanctuary and a cell. Everything we know, Earth, the neighboring planets, asteroids, comets, and even the most distant space probes, orbits within the same gravitational field, curved by the power of the sun. This force, which keeps us alive and warms the oceans, is the same one that prevents anything from truly escaping. Solar gravity is like a colossal anchor tied to the heart of the entire system. No matter how far we go, as long as we remain within its influence, we will still be prisoners of our star. This prison is so powerful that it defies any comparison with what exists on Earth. To completely escape the sun's influence, a spacecraft would need to reach speeds greater than 55,000 kilometers per hour, and even then, it would need to maintain that pace constantly, without slowing down, until crossing the limits of the heliosphere, the energetic frontier where the solar wind still dominates interstellar space. No human being has ever come close to achieving this. Even the fastest machines in history, such as the Parker Solar Probe, have not escaped. They simply orbit in bolder trajectories, but always within the sun's luminous cage. The energy required to break this barrier is so immense that it challenges the imagination. In simple terms, if we wanted to send a manned spacecraft capable of leaving the solar system, we would need a quantity of fuel greater than the mass of the spacecraft itself. Physics imposes an unbreakable tyranny. The more fuel we add, the heavier the ship becomes, requiring even more energy to move. It is a vicious circle that turns cosmic freedom into a mathematically impossible dream. Even with all the technology of the 21st century, we are still bound to the same gravity that shaped the first planets billions of years ago. Gravity, that silent force, is the true jailer of the cosmos. It does not imprison with walls, but with fundamental laws that cannot be negotiated. All mass curves space-time, and the greater the mass, the deeper the curvature. The sun, with its immensity and density, distorts the fabric of the universe around it in such a way that all bodies, large and small, remain trapped in orbits. It is as if we were inside a vast cosmic basin, and the higher we try to climb its edges, the more energy we need not to fall back. This is the nature of the solar prison, invisible, relentless, and eternal. Even light, which travels at the maximum speed allowed by the universe, feels the effects of this force. Rays of light that pass near the sun are deflected from their path, curved by stellar gravity. This means that, in a way, not even light completely escapes the sun's influence. Everything that exists within this sphere is under the dominion of a force that cannot be turned off, bypassed, or negotiated. And it is this constant presence that defines the boundary between the possible and the unattainable. To the listener gazing at the night sky, it may seem that all it would take is to accelerate a ship and follow a straight line into infinity. But in the real universe, things are not that simple. There is no absolute straight line. Every trajectory is a curve within the distorted geometry of space-time. What we call free motion is, in truth, an eternal controlled fall. The Earth falls toward the sun, but its lateral velocity is so great that it never reaches it. It merely orbits indefinitely. It is a cosmic dance of balance, and there is no easy escape from it. This illusion of infinite movement is what makes the solar system such a perfect prison. Everything appears to be in constant motion, and indeed it is, but always within precise limits. The Earth itself, which has orbited the Sun for more than 4 billion years, has never moved a single centimeter beyond the orbit that defines it. The Moon, orbiting the Earth, repeats the same fate. Everything moves, but nothing escapes. It is a dynamic prison, yet still a prison, and the key to this cell is written in the laws of physics, not in human hands. The true tragedy of this condition is realizing that our curiosity, so essential to our species, pushes us against invisible walls. We launch satellites, probes, and telescopes to try to understand what lies beyond, but all of them still circle the same central axis, the sun. It is as if a prisoner explored every corner of his cell, believing he was discovering the outside world, when in truth he was only mapping the limits of his cage. Everything we send outward remains tied by gravitational cords that pull us back to the luminous center of our confinement. Over time, we begin to understand that escaping this prison is not merely an engineering challenge. It is a direct confrontation with the structure of the universe itself. Every atom, every photon, every grain of dust is connected by the invisible web of gravity. And this web stretches infinitely without weak points. There is no way to pierce its walls because it has no walls. It is the very space in which we exist. We are prisoners not because of bars, but because we are part of the very structure of the prison. While we dream of interstellar journeys, the cosmos watches us with absolute calm. The sun will continue to spin, the planets will remain trapped, and humanity will keep trying to find cracks in the laws that govern the universe. With every failed attempt, we learn a little more about the nature of our cell. Perhaps one day in a distant future, we will understand how to bend space or distort time. But for now, the truth is simple and unavoidable. We are inhabitants of a small solar system, confined by forces as ancient as creation itself. The invisible prison of the cosmos is both our boundary and our home. And perhaps on a deeper level, that limitation is what keeps life possible. Because if total freedom existed, nothing would remain cohesive enough to form planets, seas, or consciousness. The prison is the price of stability, and understanding that is the first step toward grasping what it truly means to try to escape it. The sun is much more than a star. It is the beating heart of the solar system, the guardian of life, and at the same time, the jailer that keeps everything captive. It represents the essential duality of the universe. It creates and destroys, nourishes and imprisons, warms and limits. Nothing that exists within this system is free from its influence. Its force is so absolute that it determines the destiny of every particle of dust, every planet, and every fragment of ice that orbits within its domain. The sun is not merely a source of light, it is a living gravitational field, a presence that governs with the invisible power of physics. The mass of the sun is so immense that it represents 99.8% of all the mass in the solar system. All the planets, moons, asteroids, and comets combined do not even come close to competing with its magnitude. This disproportion creates a permanent imbalance. The sun dictates the rules, and everything else merely obeys. Even the gas giants, such as Jupiter and Saturn, are small, subdued bodies, eternally trapped in stable orbits that reveal the delicate balance between energy and gravity. If the sun were to suddenly disappear, the entire system would dissolve into chaos. But as long as it exists, its prison will remain unbroken. Solar gravity extends far beyond what human eyes can imagine. Even at the most distant frontiers, in the frozen regions of the Oort cloud, where comets orbit for millions of years before returning, it is still the sun that keeps them bound. This region can extend up to 2 trillion kilometers away. There, sunlight no longer warms, and the solar wind becomes weak and diffuse, yet gravitational influence still dominates. It is a silent reminder that the sun's power does not depend on distance. It only diminishes. It never disappears. There is no known point within our cosmic neighborhood where its presence is completely nullified. The sun exerts its power not only through gravity, but also through its constant flow of energy. Every second it releases more energy than all of humanity could produce in billions of years. This radiation is what makes life on Earth possible, but it is also what makes space a hostile environment. The charged particles ejected by the sun form what is called the solar wind, a continuous stream of energy spreading in all directions, sweeping through interplanetary space. This wind shapes the heliosphere, a gigantic bubble that envelops the entire solar system like an invisible boundary. Within it, solar influence is total. Beyond it begins interstellar space, the territory we have never conquered. The heliosphere functions both as a protective wall and a physical limit. It blocks part of the cosmic radiation coming from beyond and defines the energetic boundary between the sun and the rest of the galaxy. The Voyager probes were the first to cross this limit, and they did so only after more than 40 years of continuous travel. Even so, they remain under the sun's gravitational domain. This shows that, although we can cross its magnetic boundaries, escaping its gravity is an entirely different story. The heliosphere is merely the outer wall. The true prison is the gravitational well that the sun carves into the fabric of space-time. Physics describes this well in simple terms, but its meaning is profound. The sun bends space around itself, creating a kind of invisible valley. Everything that moves within this valley is condemned to orbit. The only way to escape would be to accumulate enough energy to climb the slopes of that valley and cross its edge, something that requires an absurd amount of energy. No current technology can generate such propulsion sustainably. It is like trying to throw a stone out of a deep, narrow well. The farther it goes, the more gravity pulls it back. This is the reality of our stellar confinement. To understand the strength that keeps us trapped, we only need to observe Earth's orbital velocity. Every second, our planet travels more than 30 kilometers around the sun. If it slowed down even slightly, it would fall toward the sun and be consumed. If it sped up too much, it would escape its orbit. But to do that, it would need to reach the solar escape velocity, about 150,000 kilometers per hour. This acceleration is so immense that it surpasses any propulsion system humanity has ever built. Not even nuclear explosions, the most powerful energy sources we know, would be enough to move an object the size of a crude spacecraft on that scale. The sun's influence goes beyond physics and reaches biology. Every form of life on Earth is a direct result of solar energy. Plants depend on light to perform photosynthesis, and animals depend on plants to exist. Even fossil fuels, coal, oil, and gas, are the result of solar energy stored over millions of years. This means that we not only orbit the sun physically, but also exist because of it on every level of reality. The prison is deeper than a matter of gravity. It is existential. We are the children of the star that keeps us captive. From a cosmological point of view, the sun is just one among hundreds of billions of stars in the galaxy, and yet it is the absolute center of our personal universe. Every thought about the cosmos, every telescope pointed into space, begins from the safety of its light. When we try to imagine life beyond the sun, we encounter not only technical barriers, but also an ancestral dependency. The human body evolved under its warmth. Our biological cycles, our sleep rhythms, the seasons, and even our metabolism are guided by it. Escaping the sun would not only be a physical leap, it would mean abandoning the matrix that shaped everything we are. Even the most ambitious technologies we have conceived still orbit within the sun's domain. Space telescopes, observation probes, and interplanetary satellites are like artificial extensions of human consciousness, yet all continue to revolve under the same gravitational field. None are free. The sun is the core that maintains the coherence of the solar system and, at the same time, the obstacle that prevents true escape. It is a cosmic irony. The star that gives us enough energy to dream of exploring the universe is the same that demands an impossible amount of that very energy to set us free. On a larger scale, the role of the sun reveals something even more unsettling. It not only imprisons planets and comets, but also dictates the rhythm of cosmic time. The entire solar system orbits the center of the galaxy at a speed of more than 800,000 kilometers per hour. Even on this colossal journey, all planets remain captive, orbiting the sun like prisoners within a ship that never changes course. The sun is both the captain and the jailer of this eternal voyage through the Milky Way. And we, as involuntary passengers, continue spinning around it, never escaping its influence. The sun is, therefore, the synthesis of cosmic duality, source and prison, creator and limiter, father and jailer. It is the fire that fuels life and the chain that prevents escape. It is the ultimate symbol of universal dependence. As long as it exists, everything within its sphere will be condemned to serve it. And paradoxically, it is precisely this luminous prison that keeps chaos at bay, allowing life to flourish on a small blue dot lost in space. The sun is humanity's golden cell, beautiful, warm, and inescapable. When we talk about escaping the solar system, the human imagination tends to fill itself with courage, adventure, and romance. We picture ships crossing space, breaking through the interstellar silence and venturing into the unknown. But reality is less poetic and more tyrannical. Escape is not a matter of will, but of energy. and the energy required to break free from the sun is so colossal that it surpasses by several orders of magnitude everything humanity has ever produced since the dawn of civilization. The universe grants no freedom without cost, and the price of escape is almost infinite. To understand this barrier, we must begin with the concept of escape velocity, the minimum speed a body must reach to free itself from another body's gravitational attraction without needing additional propulsion. In Earth's case, that velocity is approximately 40,000 kilometers per hour. To escape the solar system completely, considering the sun's gravity, the escape velocity exceeds 150,000 kilometers per hour. This means that a spacecraft would need to maintain constant acceleration until reaching that threshold, which requires an unimaginable amount of energy. No engine ever built can sustain such thrust without consuming fuel in absurd proportions. The equation that governs rocket motion, known as Tsiolkovsky's rocket equation, reveals the true dilemma of space exploration. It shows that the more speed we want, the more fuel we must carry. But the more fuel we add, the heavier the spacecraft becomes, and the more energy is needed to move that additional mass. The result is a self-destructive cycle, an endless search for energy that grows faster than our ability to generate it. This is the fundamental paradox that keeps humanity trapped within the solar system. It is not a lack of courage, but the mathematical dictatorship of physics. Even the most powerful rockets ever launched by humanity, such as the Saturn V and the Falcon Heavy, are minuscule in the face of this challenge. The Saturn V, responsible for taking astronauts to the moon, could accelerate the spacecraft to about 39,000 kilometers per hour, enough to escape Earth's gravity, but still far below what is needed to leave the solar system. Even if such a ship were continuously propelled, fuel consumption would increase exponentially until the entire system collapsed under its own weight. Physics is merciless, and every attempt to escape demands more than can possibly be supplied. The energy required to propel a spacecraft to interstellar speeds is almost incalculable. To move a vessel of only 1,000 tons to 1/10, the speed of light would require the equivalent of all humanity's energy production over hundreds of thousands of years. This is because kinetic energy grows with the square of the velocity. Doubling the speed does not double the energy cost. It multiplies it. Every additional kilometer per hour exacts an ever higher price. That is why, in practice, interstellar travel remains confined to science fiction. Classical physics imposes an almost impassable wall, and it is not only a matter of fuel. Even if it were possible to generate enough energy, another problem would arise: heat dissipation. Continuous acceleration generates intense heat in any physical system, and in the vacuum of space there is no easy way to release it. The spacecraft would heat up to the point of melting or disintegrating. Theoretical solutions involve thermal shields and active radiation systems, but all add weight and complexity, worsening the original problem. It is a circle of limitations that feeds itself. Each attempt to solve one obstacle creates another, even greater. The term delta V, used by aerospace engineers, defines the sum of all velocity changes required to complete a mission. It is the true measure of difficulty in any space journey. And when we apply this concept to the escape from the solar system, the number becomes prohibitive. To escape completely, a spacecraft would need a delta V greater than any human vehicle has ever achieved. This is not merely a technological problem, it is a physical wall built by the universal laws of energy and mass. To grasp the scale of it, Voyager 1, launched in the year 1977, is the fastest human-made object ever created. Even so, it travels at just over 60,000 kilometers per hour, and it took more than 40 years to reach the edge of the heliosphere. Compared with the velocity required to fully escape the sun's gravity, it is a cosmic tortoise. If it wanted to reach the nearest star, Alpha Centauri, it would take more than 70,000 years, and that is assuming no decelerating forces acted upon it during the journey. The mathematics is relentless. The universe is far too vast and we are far too small. Beyond the energy barrier, there is the matter of time. Even if we could build a spacecraft capable of reaching a significant fraction of the speed of light, the time needed to cross interstellar space would still be measured in decades, centuries, or millennia. And the faster a ship travels, the harder it becomes to shield it from cosmic dust and particles, which at high velocities behave like lethal projectiles. The impact energy of a single grain of dust, at a fraction of light speed, would be enough to destroy an entire spacecraft. This means that even with unlimited energy, the cosmos still imposes practical barriers that current technology cannot overcome. Energy, therefore, is humanity's true battlefield. It defines what we can and what we will never reach, and for now it is insufficient to free us from the sun's domain. Every rocket we launch is like a stone hurled toward the sky, impressive yet destined to fall back. Earth, the moon, Mars, Jupiter, all are bound by the same invisible chains. The sun keeps us within a cage of energy and gravity, and everything we have built so far merely allows us to jump a little higher inside it. In essence, escaping the solar system is not merely an engineering problem, it is a direct confrontation with the limits of thermodynamics. The second law, which governs entropy and the flow of energy, dictates that no system can operate without losses. Every thrust, every explosion, every drop of fuel wastes part of its energy as heat, vibration, or radiation. The result is that we can never convert 100% of our fuel into useful motion. There is always a cost. And in the universe, that cost is what separates dreams from reality. It is fascinating to realize how this limitation is written into our very nature. We are biological beings bound to a planet made of carbon and water, attempting to defy the same forces that shaped our existence. The energy we seek to escape comes, ironically, from the very sun that confines us. It is like trying to use the jailer's keys to open a cell that he himself keeps reinforcing. And perhaps that is why, even with all our technology and imagination, we continue to orbit around the same bright point that witnessed the birth of life. The energy cost of escape is, therefore, more than a technical obstacle. It is a cosmic lesson about the balance between power and limitation. The universe seems designed to allow motion, but not complete escape. Everything spins, everything orbits, everything returns to its point of origin. And perhaps that is the greatest irony of physics. The more we try to conquer the infinite, the more it reveals that our freedom is only a well-structured illusion. Humanity has learned to hurl fire into the sky, yet still crawls before the vastness of the cosmos. When we think of space missions, towering rockets and stunning images of Mars, it may seem as though we have mastered space. But the truth is that everything we have achieved so far amounts to a small leap within the backyard of the solar system. None of our engines, no matter how advanced, comes close to the power required to break free from the sun's grasp. The barrier is not only physical, it is technological. Our machines are fragile before the immensity of the cosmos, and our solutions so far merely scratch the surface of the problem. The chemical engine, the heart of all modern rockets, relies on the same basic principle used since the 20th century, the controlled combustion of liquid or solid fuel to generate thrust. This form of propulsion depends on chemical reactions that convert stored energy into hot gases expelled at high speed. But the efficiency of this process is limited by the laws of thermodynamics. Even in the most modern models, such as the Falcon Heavy, only a small fraction of the fuel's energy is converted into useful motion. The rest is lost as heat, vibration, and noise. This inefficiency creates a technological ceiling that makes any attempt at interstellar travel based on combustion unfeasible. The ratio between fuel and payload is another insurmountable obstacle. To send a small satellite to Mars, a rocket requires hundreds of tons of fuel. The Saturn V, which carried astronauts to the moon, weighed almost 3,000 tons, more than 95% of which was fuel alone, and that was to reach a celestial body relatively close, less than 400,000 kilometers away. If we tried to use the same method to send a ship into interstellar space, we would need a rocket larger than any structure ever built, a monster of metal and energy impossible to launch from Earth's surface. Space engineers have tried to overcome these limitations by creating more efficient engines, such as electric propulsion. Instead of burning fuel, these engines accelerate ions, electrically charged particles, using magnetic fields. They produce very little thrust, but it is continuous, allowing great speeds to be achieved over long periods. This is the principle used by the Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres. However, these engines depend on constant electrical energy sources, usually solar panels, and the farther a spacecraft travels from the sun, the less energy it receives. Efficiency drops, thrust decreases, and the journey becomes eternally slow. The technology is elegant, but insufficient when faced with cosmic distances. Another advance has been nuclear propulsion. The idea is to use the fission or fusion of atoms to generate heat and thus thrust. This technology promises far greater efficiency than chemical engines and could theoretically allow interstellar travel within human timescales. But in reality, nuclear reactors are complex, dangerous, and difficult to control in space environments. The risk of contamination, along with political and ethical barriers, has slowed the development of such systems. Even promising projects such as NERVA, developed by the United States between the years of 1960 and 1970, were abandoned before leaving the drawing board. Fear overcame ambition. There is also the problem of miniaturization. Any propulsion system must balance power, weight, and efficiency. The more energy an engine produces, the heavier it becomes, and the lighter the engine, the weaker its thrust. It is a dilemma with no apparent solution. Attempts to create hybrid thrusters that combine chemical combustion with electrical energy have yielded marginal gains, but remain far from enabling interstellar travel. The energy barrier remains intact, a wall of iron surrounding the solar system. The limitation of current technologies lies not only in the engines, but also in the materials that make up the spacecraft. To withstand long interstellar journeys, a ship would need to resist cosmic radiation, extreme temperature variations, and the continuous pressure of deep space. No known material can maintain its structural integrity for centuries or millennia. Metals degrade, electronic systems fail, and prolonged exposure to the vacuum of space causes molecular deterioration. Even a journey of 100 years would require engineering that remains beyond our practical understanding. It is not enough to accelerate. One must endure. Fuel, another essential element, is a prison within the prison. Every spacecraft must carry its own energy reserve, and this requirement limits its range. Even electric engines depend on solar energy or nuclear generators, both of which have finite lifespans. When the source is exhausted, the ship dies. This is what is slowly happening with the Voyager probes, whose plutonium reactors are fading after decades of operation. Soon they will become nothing more than metal shells drifting in the dark, silent symbols of a humanity that tried to flee but was slowly defeated by time and entropy. Some theoretical projects attempt to imagine radical solutions, such as the use of solar sails. In this concept, enormous ultra-thin panels would capture the pressure of sunlight to push the spacecraft forward. It would be a way of using the jailer's own force as a means of escape. But in practice, this idea faces colossal obstacles. Radiation pressure is extremely weak, and a sail spanning kilometers would be required to generate significant acceleration. Moreover, the sail would lose efficiency as it moved away from the sun, becoming useless in the outer regions of the solar system. The irony is cruel. The only free energy available is also the one that fades precisely when we need it most. Another challenge is control and precision. The farther a spacecraft travels, the harder it becomes to maintain contact and adjust its trajectory. The radio signal sent from Earth may take hours, days, or even weeks to reach it, depending on the distance. This means that every maneuver must be calculated in advance and executed autonomously. The delay in communication turns space into a silent ocean where each wrong decision can mean the end of the mission. It is like trying to steer a ship through a storm without being able to see the horizon. Scientists also face philosophical limitations. The physics we know was built upon the observable laws of our local universe, the same laws the sun imposes within its sphere. Perhaps there are deeper, undiscovered principles capable of transcending these restrictions, but until they are found, we remain bound to the paradigm of conventional energy. All we can do is refine, step by step, the technologies we already master. And each advancement, no matter how promising, only reveals how far we still are from true cosmic freedom. Technological barriers are reflections of our own limitations. They represent the point where the human dream collides with the reality of physics. From the first gunpowder rockets to the interstellar probes, the entire history of space exploration is a struggle against the impossible. Every centimeter conquered beyond Earth is a victory wrested at the cost of centuries of science and billions of units of energy. And even so, we have not come close to the real frontier, the sun's gravitational limit. The truth is that the cosmic prison is not just a metaphor, it is a measurable fact. a direct consequence of the energetic structure of the universe. Every engine, every rocket, every spark of propulsion is an attempt to break one of nature's oldest laws. But for now the cosmos wins. Humanity remains chained to its star, dependent on a technology born to look upward, but not to cross the infinite. And as the fire of rockets fades in the sky, the sun continues to watch, silent and patient, keeping all its prisoners orbiting under its eternal light. In the entire history of humanity, only 2 human creations have managed to surpass the most distant boundaries of the solar system. No living being, no crude spacecraft, no triumphant flag accompanied these journeys. They were solitary, silent, and stubborn machines. Their names are known to everyone who studies deep space. Voyager 1 and Voyager 2, 2 small probes launched in the 1970s, powered by plutonium reactors and by human curiosity. They are the only witnesses to have crossed the frontier between the sun's domain and interstellar space. And even so, they remain bound to their old gravitational master. The Voyager project was born in an era when scientific optimism seemed limitless. In the year 1977, the North American Space Agency decided to take advantage of a rare planetary alignment that occurs only once every 176 years. This alignment would allow a single probe to visit Jupiter, Saturn, Uranus, and Neptune by using the gravitational pull of these planets, a maneuver known as gravitational assist. It was like using the gravitational fields of the gas giants as a kind of cosmic slingshot, stealing part of their orbital energy to accelerate the spacecraft. This technique would become one of the most elegant tricks in modern space engineering. The 2 probes were launched just days apart. Voyager 2 departed first on August 20th, 1977, and Voyager 1 followed shortly after on September 5th. Both carried the same mission: to explore the outer planets and, if possible, continue beyond them. Each probe measured about 3 meters wide and weighed just over 720 kilograms, a modest structure considering the scale of the challenge. Inside them, precise scientific instruments observed magnetic fields, atmospheric compositions, and solar wind particles. But the true legacy of the Voyagers would not be what they saw. It would be what they came to represent over time. Voyager 1, after passing by Jupiter and Saturn, gained enough momentum to escape the orbital plane of the planets. Its destination, interstellar emptiness. Today, it is the most distant object ever created by human hands. It is more than 24 billion kilometers from Earth, traveling at a speed of about 60,000 kilometers per hour. This means that, even moving at that constant velocity, it would take more than 70,000 years to reach the nearest star, Alpha Centauri. The probe no longer sends images, only data about deep space, particles, radiation, and the magnetic silence beyond the heliosphere. In the year 2012, Voyager 1 officially crossed the frontier of the heliopause, the region where the solar wind no longer has the strength to push against the interstellar medium. It was the first human-made artifact to enter interstellar space. The event was historic, but also deeply symbolic. Humanity had, at last, surpassed the boundary of the sun, but only with a metallic messenger traveling without destination and without return. Even beyond the heliosphere, the sun's gravity still acts upon it. The probe continues to orbit the sun, though in an extremely elongated trajectory. Technically, it is not free. It merely follows a path so distant that its return will never occur within the scale of human time. Voyager 2, in turn, followed a different path, visiting the 4 gas giants before also heading toward the outer reaches of the solar system. In the year 2018, it became the second human-made object to cross the heliopause. Though slower than its sister, it carries the same symbol of perseverance and isolation. The 2 probes travel in opposite directions, like messages cast in bottles across the cosmic ocean. Both continue to transmit intermittent data, powered by nuclear reactors that are slowly fading. Soon, when their energy is completely exhausted, they will fall into absolute silence and continue drifting forever, with no one left to know where they are. These probes represent more than scientific missions. They are monuments to human persistence and solitude. Each carries a Picasso golden record, known as the Golden Record, containing sounds, images, and greetings from different cultures on Earth. The idea, conceived by astronomer Carl Sagan and his team, was to make the voyagers eternal ambassadors of humanity. On the record are recordings of music, greetings in more than 50 languages, and even the sound of a human heartbeat. A poetic, perhaps naive gesture, given that the odds of the record being found by another civilization are practically zero, but the gesture itself is grand, an attempt to leave a trace of consciousness in the infinite. The journey of the voyagers is proof of human ingenuity, but also a confession of powerlessness. Nearly 50 years after their launches, they remain the only messengers beyond the heliosphere. No new probe has followed them. No modern mission has surpassed their achievements. This reveals how monumental that effort was, and how far we have retreated in interstellar ambition. Today, most space agencies focus on closer goals: Mars, the Moon, asteroids. The deep cosmos remains an unreachable realm, reserved only for the two small ships still crossing the abyss in our name. Even at their almost inconceivable distances, the voyagers remain under the Sun's dominion. The Sun's gravitational pull extends to about 2 trillion kilometers, far beyond where they are now. This means that ultimately they still orbit the Sun. Their trajectories are merely infinitely long lines within the curvature of solar spacetime. Complete escape would be impossible without reaching the ultimate escape velocity, something that would require more energy than the probes ever possessed. Thus, they travel forever, but never truly free. There is a tragic beauty in this realization. The voyagers embody humanity's desire to transcend boundaries, but also the inevitability of cosmic frontiers. Every meter they travel is a reminder that freedom in the universe is relative. Even when we believe we have escaped, we remain under some invisible force, bound by laws greater than ourselves. The universe allows movement, but not complete emancipation. The voyagers are the materialization of that truth, eternal travelers in a prison without walls. They drift away millimeter by millimeter as Earth spins in silence. The signal they send today takes more than 20 hours to reach us, a faint distorted radio echo crossing the void before being captured by giant antennas. It is the last thread connecting us to them. One day, that thread will break. When the last bit of information is received, the bond between the Sun and its fugitives will finally fade. But even then, they will not be free. They will continue traveling through endless silence, carrying the message of a species that dreamed of escaping its luminous prison. The Voyager probes proved that escape is possible in theory, but unattainable in essence. They left the solar system, but not the Sun. They are like leaves carried by the cosmic wind, still under the influence of the same gravitational field that has kept the planets dancing for billions of years. And thus, between hope and despair, they continue forward, eternal and solitary, reminding humanity that the universe allows the dream of escape, but never the escape from the dream. Every human attempt to escape the solar system collides with the same invisible wall: energy. It is the most precious commodity in the universe, the currency with which everything is bought: motion, light, heat, and life. And it is also the cruelest limit, the point where willpower meets reality. In space, there are no shortcuts or tricks. Every meter traveled comes with an energy price, and that price grows exponentially as we move away from the Sun's influence. Energy is the true cosmic jailer, and its laws are non-negotiable. At the heart of it all lies the relationship between mass and energy, expressed by Albert Einstein's famous equation: energy equals mass, multiplied by the speed of light squared. This simple relation reveals something terrifying, that even a small amount of mass contains enough energy to move entire worlds, yet releasing that energy in a controlled way is almost impossible. Nature guards this secret with absolute rigor. The only events that perform this complete conversion are nuclear explosions and the reactions that power the stars. And even those titanic forces obey the same fundamental restrictions. Nothing can exceed the speed of light, and every acceleration carries an increasing cost. Kinetic energy, the energy of motion, is the core of the equation of cosmic freedom. It grows with the square of velocity, meaning that to double a spacecraft's speed, one must quadruple the energy expenditure. On astronomical scales, this quickly becomes unfeasible. To propel a spacecraft of 1,000 tons to a significant fraction of the speed of light would require an amount of energy comparable to what the Sun emits in several seconds, a figure so absurd that it defies any practical possibility. And even then, that energy would only set the ship in motion. It would not guarantee its deceleration or survival along the way. Energy also imposes a natural limit on the size of civilizations. No matter how advanced a species becomes, it can never control more energy than that produced by its own star. This is what astrophysicist Nikolai Kardashev proposed when he created his famous scale of cosmic civilizations. Humanity, with all its power plants, dams and reactors, still occupies the lowest level on that scale, consuming only a minuscule fraction of the energy available on its planet. To harness all the power of a star, we would need a colossal structure such as the hypothetical Dyson sphere, enveloping the sun and capturing all its radiation. But even if that were possible, we would still be trapped inside the same luminous cage, only with more energy to wander within it. The energy dilemma is not only about obtaining fuel, but also about how energy behaves in space. In the vacuum, there is no medium to transfer heat, making thermal dissipation an almost unsolvable challenge. Every time an engine operates, part of its energy turns into residual heat. If that heat is not removed, it accumulates, overheating the ship to the point of collapse. And the more energy we use to accelerate, the more heat we generate. This is one of the silent barriers of space exploration, a thermal trap that makes it impossible to operate extremely powerful engines for long periods without destroying the very system they power. There is also the problem of storage. Energy must be contained, and the denser it is, the more dangerous it becomes. Chemical fuels have low energy density. Nuclear fuels, though more powerful, are unstable and hazardous. Antimatter, theoretically the most efficient form of energy known, releases 100% of its mass as pure energy. But producing even a few milligrams requires colossal amounts of electrical power. It is the paradox of efficiency. The more powerful the energy source, the more impossible it becomes to produce it on a usable scale. Thus, humanity finds itself trapped in a cycle where every advance reveals a new abyss. Special relativity imposes the final barrier. As an object approaches the speed of light, its effective mass increases, demanding ever greater amounts of energy to keep accelerating. To actually reach the speed of light, the energy required would be infinite. This means that no matter how much we advance technologically, we will never be able to surpass this frontier. The universe has imposed an absolute limit on freedom. Light is the ceiling of physical existence, the maximum rhythm at which any information, particle, or ship can move. It is as if the cosmos had drawn a line on the floor and declared, "You shall not cross." This restriction creates fascinating and unsettling consequences. Even if a ship could approach the speed of light, time inside it would flow more slowly compared to the external world, a phenomenon known as time dilation. For the crew, the journey might feel like only a few years, but for those who remained on Earth, centuries or millennia could pass. This means that any interstellar voyage near the speed of light would transform its travelers into ghosts of time, able to witness the future but never return to the present. Energy, in this case, not only limits space, it bends time itself. Energy also defines the reach of our boldest dreams. Every engine, every probe, every interstellar project is, at its core, an attempt to negotiate with energy. We crave more power, more speed, more freedom. But the universe grants no favors. It demands balance. Energy is never created nor destroyed, only transformed. And every transformation exacts a price. That is why, when we talk about escaping the solar system, we are truly talking about trying to deceive one of the most unforgiving laws of nature. To this day, no known civilization has succeeded in doing so, and perhaps none ever will. Human attempts to master energy are grand, but still primitive. We have learned to control fire, electricity, and nuclear fission. Yet all of this is merely a glimpse of what the cosmos itself can unleash. The stars transform billions of tons of matter into energy every second, powered by processes that defy imagination. In comparison, our technologies seem fragile and infantile. We use chemical explosions to try to break out of a prison built from the very fabric of space-time. It is like trying to shatter a diamond with bare hands. The true drama of energy is that it is both the engine and the limit of existence. Everything that exists is, in essence, energy in different forms, condensed into matter, transformed into light, converted into motion. And yet, that same energy confines us, preventing us from reaching infinity. The sun, by giving us life, also traps us. The earth, by sheltering us, also isolates us. We are prisoners of an energetic system that allows us to exist but not to escape. Energy, therefore, is the supreme paradox of the universe. It is what moves galaxies and what prevents us from crossing them. It is what gives shape to space and what defines its boundaries. It is the foundation of all physical laws and the sentence that keeps us under cosmic custody. The universe does not imprison us out of cruelty, but out of coherence, because in the end, every attempt at escape would violate the energetic harmony that sustains all that exists. Humanity still dreams of the day this barrier will be broken. We speak of warp drives, of negative energy, of exotic matter, of propulsion systems that distort the fabric of space. But all these ideas, no matter how brilliant, still depend on the same thing: energy. And as long as it obeys the laws we know, the universe will remain as it is, vast, silent, and unreachable. Energy is the invisible wall between us and infinity. And perhaps the greatest mystery of the cosmos is precisely this, that even within this luminous prison, we can still look up at the sky and wish for more. This barrier also distorts our notion of causality. At speeds close to that of light, time slows down for the traveler, but continues advancing normally for the one who remains still. This means that two observers can disagree about the order of events, depending on their relative velocities. Time ceases to be absolute. The past, present, and future become concepts dependent on motion. Relativity transforms the universe into a tapestry where time is woven together with space, and each point in that tapestry vibrates to its own rhythm. The energy required to accelerate a body to the speed of light grows infinitely. Each increment of speed demands more energy than the previous one. The faster a body moves, the harder it becomes to accelerate. This relationship is what prevents any spacecraft from ever reaching the speed of light. If we tried to move a manned ship at that speed, its mass would increase indefinitely, requiring an amount of energy that the universe itself could not provide. That is why the light barrier is so absolute. It is not merely a theoretical boundary, but a mathematical consequence of the very structure of space-time. Even so, humanity insists on dreaming. People speak of warp drives, space-time tunnels, quantum shortcuts that could bypass the limitation of light. But all these concepts so far remain in the realm of hypotheses. No experimental evidence has ever confirmed the possibility of breaking or circumventing the speed of light, and perhaps it never will. The speed of light is like the maximum tempo of existence itself, the beat with which the universe measures time and space. There is also a philosophical dimension to this limit. It defines the scale of human experience. We live in a universe where everything moves at finite rhythms, and that creates the notion of time, aging, and history. If we could surpass light, time would cease to make sense. There would be neither past nor future, only an eternal, frozen present. The speed of light is what separates motion from stillness, matter from eternity. Without it, the universe would be a formless chaos. It is possible that this limitation is not a punishment, but an essential structure that makes reality understandable. Light, therefore, is the frontier between what is and what could be. It is the sum of all physical possibilities. Everything that exists happens below its velocity. Everything that could exist beyond it remains in the realm of abstraction. When we look at the brightness of the stars, we are gazing at the very wall of possibility, and perhaps that wall exists not to confine us, but to give us a horizon, a line that invites us to think, to dream, and to challenge the impossible, even knowing it cannot be reached. The speed of light is the supreme limit, but also the most poetic reminder of our condition. We are slow creatures in a fast universe, trying to reach something that travels without time. Even if we can never match its speed, we can follow its direction. That is what we do every time we ignite a rocket, a telescope, or an idea. Ironically, it is light, this insurmountable limit, that illuminates the path of all our attempts at escape, and thus light remains the greatest paradox of the cosmos. It is both prison and key, obstacle and inspiration, the limit that defines life and the beacon that points toward infinity. In the end, perhaps we do not need to surpass it to understand the universe. Perhaps the true secret lies in learning to walk beneath its shadow, realizing that the same radiance that guides us is also what keeps us within the contours of the real. Distance is the most silent and relentless enemy of the cosmos. It does not scream, it does not move, and it does not attack. It simply exists, invisible, cold, and indifferent. It is distance that separates worlds, civilizations, and possibilities. It is what turns the dream of exploration into an endless march against the void. Even if humanity were to master all available energy, even if we built engines capable of bending space-time, we would still face the same problem. The universe is simply too vast. Immensity itself is the true prison. Space, in its colossal vastness, is the frontier that no willpower, no matter how powerful, can truly cross. To grasp the scale of this struggle, one must abandon every human notion of distance. The solar system, for example, seems small when seen in diagrams, but its true extent is almost inconceivable. Earth is 150 million kilometers from the Sun, a distance so great that light, traveling at 300,000 kilometers per second, takes about 8 minutes and 20 seconds to reach us. If the Sun were to vanish this instant, we would only notice its absence 8 minutes later, and that is merely the first step of the cosmic staircase. The farthest planet, Neptune, orbits the Sun at approximately 4,500 million kilometers away. And yet, that is still the inner solar system. The true boundary lies much farther out, within the Oort cloud, an immense sphere of frozen debris that may stretch up to 2 trillion kilometers. This region marks the final vestige of the Sun's gravitational influence, the threshold where the solar wind ceases to blow, but gravity can still be faintly felt. It is there that the Sun's dominion finally dissolves into interstellar emptiness, and crossing that boundary is a task that, to this day, only 2 probes have attempted, and neither has truly escaped. But what comes after the Oort cloud is the real abyss. The space between stars is not just vast, it is disproportionate to the human scale. The closest star to us, Proxima Centauri, lies more than 40 trillion kilometers away. Even traveling at the speed of the Voyager 1 probe, it would take more than 70,000 years to reach it. 70,000 years, the time between the first cave paintings and the present day. Each star, every shimmering point in the night sky, is isolated by distances so absurd that they render any form of direct contact virtually impossible. The universe is an archipelago of suns, separated by oceans of nothingness. These distances are not merely a practical challenge, but also a psychological and philosophical limit. The human mind was not made to comprehend such enormous scales. Our brains evolved to measure what fits within the scope of the body, the field, or the mountain, not to deal with trillions of kilometers. That is why space feels abstract. There is no meaningful reference. When we say something is light years away, we are describing a unit that has already lost its connection to human experience. Space is too immense even to be imagined, and what cannot be imagined can hardly be conquered. Even if we could travel at a significant fraction of the speed of light, distance would still remain a sentence of isolation. At 100,000 kilometers per second, a third of the speed of light, it would take more than 13 years to reach the nearest star. And that does not include the time needed to slow down, correct the trajectory, or survive cosmic radiation. Interstellar travel, when viewed through the lens of distance, ceases to be an adventure and becomes something almost metaphysical, a crossing through an endless desert where time and space blend into a silent eternity. Scientists try to find theoretical solutions for this abyss. They speak of generation ships, enormous self-sustaining colonies that would travel slowly over centuries, with crews replaced by successive generations. The idea is to turn the journey into a way of life. The ship would become a new planet, a civilization in motion, where births and deaths would occur as the destination drew closer, millimeter by millimeter. It is a poetic yet cruel proposal, because in practice, these generations would never know Earth, and perhaps would never reach their final destination. In that sense, the universe becomes a moving prison. Other theorists propose world ships, gigantic artificial habitats orbiting distant stars, carrying entire ecosystems within them. These megastructures would, in theory, be sanctuaries capable of enduring both time and distance. But even if they were possible, the challenge would remain the same: moving them. The energy required to propel such a colossal structure between stars is immeasurable, and the more we advance in our ideas, the clearer it becomes that the barrier of distance is also the barrier of energy. Space does not resist our passage, it simply refuses to be crossed. The vastness of the universe also creates a temporal problem. When we observe galaxies billions of light years away, we are seeing images from a distant past, the universe as it was billions of years ago. This means that the cosmos we see today no longer exists in the same form we observe. Each point of light is an echo, and at the same time everything we emit now, our radio signals, our lights, our words, will spread eternally, but diluted, weak, almost imperceptible. The probability that another world might hear us is almost zero. Distance is a silence that erases even the sound of existence. Space engineers often say that the greatest obstacle to exploration is not speed, but time, because distance turns every journey into an event that exceeds a human lifetime. Even if we could build a ship capable of accelerating to 10% of the speed of light, the voyage to the nearest star would still take 40 years. 40 years of acceleration, solitude, and waiting. And the return, if it ever happened, would take the same amount of time. Distance is the reason why space feels infinite, because it cannot be lived, only observed. The universe is, at its core, a system of separations. Each star is an isolated sun, each planet a lost island in the ocean of space-time. Light, with all its speed, is merely the messenger that crosses these abysses, carrying fragments of information from one corner to another. And we, confined to our star, watch it all from afar, condemned to live as spectators of infinity. The war against distance is, in truth, a war against the very structure of the cosmos, for space is not empty. It is the battlefield where time and energy wage an eternal struggle for dominance. Even so, we continue to fight. We launch increasingly powerful telescopes, probes that advance a few kilometers per second, antennas that capture echoes from billions of years ago. It is a silent resistance, a refusal to accept confinement. Every scientific breakthrough is a small step in this endless war. Perhaps we will never conquer distance, but continuing to try is itself a way of defying it. Because deep down, the desire to reach the unreachable is what defines the essence of humanity. Distance is the way the universe teaches us humility. It reminds us that we are small, fragile, and finite. But it also shows that we are capable of looking at infinity and still dreaming. The war against distance is not won with engines or energy, but with imagination. It is the curious gaze of the human being, pointed toward the sky, that breaks the silence of space. And as long as that gaze exists, distance, no matter how vast, will never be a defeat, but merely an invitation to keep trying. Among all the ideas humanity has conceived to break through the limits of the solar system, none has been as promising and at the same time as feared as nuclear propulsion. Since the earliest days of the space age, scientists have dreamed of using the power of the atom not only to generate electricity, but to propel spacecraft toward the stars. The energy contained within the nucleus of atoms is almost unimaginable, millions of times greater than any chemical reaction. Mastering that power would mean freeing ourselves from the tyranny of conventional fuels. But the story of nuclear propulsion is also the story of a dream humanity did not have the courage to fulfill. It all began in the decades of 1950 and 1960, when enthusiasm for nuclear energy was at its peak. The world believed the atom would be the key to a new era. It was in this context that the Pi-G, Project Orion, was born, one of the boldest ideas ever conceived. The proposal was simple yet brutal: to use nuclear explosions to push a spacecraft through space. Each bomb detonated behind the ship would generate a colossal impulse, gradually accelerating it to speeds never before achieved. In theory, a ship powered by this method could reach up to 10% of the speed of light. It would be the first truly interstellar machine. The concept, as shocking as it may sound, had solid foundations. Physicist Freeman Dyson and his team calculated that a spacecraft weighing only a few hundred tons, propelled by nuclear detonations, could reach Saturn in just a few months and leave the solar system within a few years. Simulations indicated that the impulse from a single explosion would be enough to move the craft several kilometers per second. It was an ingenious solution, using the destructive power of atomic weapons to transcend Earth itself. The engine of the apocalypse became the key to cosmic freedom. But the dream soon collided with its own moral and political dilemmas. Detonating hundreds of atomic bombs in space, even along controlled trajectories, represented an unacceptable risk. The Pratwent Partial Nuclear Test Ban Treaty, signed in 1963, ended any possibility of continuing the project. A world that feared nuclear annihilation was not ready to accept it as a tool for exploration. Thus, Project Orion was abandoned before ever leaving the drawing board. Humanity chose safety over ambition, and perhaps that choice sealed our fate within the solar prison. Even after Orion's end, the idea of using nuclear energy for propulsion did not die. In the years that followed, the National Aeronautics and Space Administration and other space agencies invested in safer alternatives, nuclear thermal fission reactors. Instead of detonating bombs, these engines would heat a gas such as hydrogen, expanding it through a nozzle to produce thrust. This technology promised to be up to twice as efficient as chemical engines. The most famous project was NERVA, meaning Nuclear Engine for Rocket Vehicle Application, developed between the years of 1961 and 1972. It was even tested on the ground, proving that the concept worked. But once again, fear prevailed. The risk of accidents and the enormous costs led to its definitive cancellation. The following decades brought even bolder proposals, based not on fission, but on nuclear fusion, the very process that powers the stars. If we could reproduce that reaction in a controlled way, we would have access to an almost infinite source of energy. The fusion of light isotopes such as deuterium and tritium releases enormous amounts of energy without the same radioactive waste produced by fission. A spacecraft powered by fusion could accelerate continuously for years, reaching speeds that would make interstellar travel at least conceivable. Projects such as Daedalus, developed by the British Interplanetary Society in the decade of 1970, imagined giant ships powered by microfusion explosions, a miniature stellar power plant traveling through the void. But, as with so many other human dreams, the abyss between theory and practice proved insurmountable. To this day, controlled fusion remains a colossal technical challenge. It requires temperatures of millions of degrees Celsius and perfect plasma confinement, something no current technology can sustain long enough. If maintaining a stable fusion reactor on Earth is difficult, doing so aboard a spacecraft is almost unthinkable. The stellar engine remains only a distant vision, a promise trapped within equations. There is also the political and environmental dilemma. Any project involving nuclear material faces immediate resistance. The fear of contamination, the risks of accidents, and the memories of atomic destruction have shaped a global aversion to anything bearing the name nuclear. Launching a rocket containing reactors or active warheads would be considered a civilizational risk. Space, ironically, has become a sanctuary that cannot be defiled by the same energy that powers the stars. The sun may burn freely, but we cannot. Even the safest experiments, such as the nuclear generators aboard the Voyager and Cassini probes, are modest examples of what could be achieved. These devices, called radioisotope thermoelectric generators, use the heat from plutonium decay to produce electricity. They do not generate thrust, only electrical power to run instruments. They are timid remnants of an era that dreamed too high. True nuclear propulsion, capable of moving interstellar ships, remains only a ghost in the archives of history. The failure of nuclear propulsion is more than a technical limitation. It is a metaphor for the human condition. We once held the energy of the stars in our hands, but we were unable to use it without fear. The same force that could free humanity could also destroy it, and faced with that duality, we chose caution. Perhaps it was wisdom, perhaps cowardice. Either way, the result is the same. We remain confined. Nuclear energy has shown that escape is possible but morally unbearable. To break free from the solar prison, we would have to master not only physics, but also the responsibility of wielding the power of the stars. Until that happens, we will continue to gaze at infinity with our feet anchored to Earth, aware that the secret of liberation lies within the atom itself, and that it still frightens us more than the void. If nuclear energy represents the fire of the stars, antimatter is the primordial lightning, the purest and most devastating manifestation of energy that physics can conceive. In theory, it is the perfect fuel. A single collision between a particle of matter and its antimatter counterpart releases 100% of their combined mass as pure energy. Nothing wasted, nothing turned into useless heat, only light, motion, and absolute power. It is the ideal conversion between mass and energy, the tangible realization of Albert Einstein's equation. If it could be safely stored, a small amount of antimatter could power an interstellar ship across distances that today seem unreachable. But between theory and practice lies an abyss almost as vast as the space it promises to cross. Antimatter is the most expensive, rare, and dangerous material in the universe. It does not exist naturally in large quantities. It is only produced in extreme events, such as stellar explosions or cosmic ray collisions. On Earth, we can only create it artificially, inside giant particle accelerators like the Large Hadron Collider in Switzerland. There, protons are accelerated to near light speed and collide, releasing a minuscule amount of antimatter for just fractions of a second. The total amount ever produced barely reaches a few nanograms, enough to power a light bulb for less than 1 second. The real difficulty lies in storing it. When antimatter comes into contact with ordinary matter, it annihilates instantly, releasing energy in the form of gamma radiation. This means it cannot touch the walls of any physical container. To keep it stable, scientists must use perfect magnetic fields that hold it suspended in absolute vacuum without touching anything. These devices, known as penning magnetic traps, require a constant supply of energy to function. A minimal failure, an electrical fluctuation, a short circuit, or a shutdown, and all stored antimatter would annihilate in a fraction of a second. On a practical scale, it would be like maintaining a bomb of pure energy permanently on the brink of explosion. Still, scientists continue to dream. The calculations are too seductive to ignore. A single gram of antimatter could produce the same amount of energy as tens of tons of chemical fuel. That means, in theory, a spacecraft powered by antimatter could reach significant fractions of the speed of light. Unlike conventional engines, it would not depend on slow reactions or massive fuel tanks. Only small, precisely controlled quantities would be enough. Such a ship could cross the solar system in days and reach nearby stars within decades. It would be the ultimate liberation from solar gravity, the boldest step humanity has ever imagined. But antimatter is not just a technological challenge, it is also an economic and philosophical one. Producing a single milligram would cost trillions of monetary units and consume more energy than the entire annual electrical generation of several countries combined. It is an investment without practical return, at least with today's technology. Even if costs could be reduced, storage and transportation would remain nearly impossible. Any failure during launch, any impact, any accidental contact with matter, and the resulting explosion would be equivalent to that of a nuclear bomb. The energy of liberation would become the energy of destruction. Scientists estimate that to move a 1,000-ton spacecraft to 10% of the speed of light, it would take around 10 tons of antimatter, an absurd number, unreachable by any means currently available. And even if it were possible to create that much, keeping it confined during a decades-long voyage would be a constant risk. Antimatter is unstable not because it decays on its own, but because the entire universe is its enemy. Everything around it, air, metal, even dust, is made of matter, and the slightest contact would trigger total annihilation. Still, some see in antimatter the key to the future. Theoretical researchers already discuss concepts such as the catalyzed antimatter engine, in which small quantities would be used to ignite controlled nuclear fusion reactions, combining the power of the two greatest energy forces known. In that model, antimatter would not serve as the main fuel, but as the detonator for a larger, more stable reaction. It would be a way to tame lightning itself, turning chaos into control. Yet the challenge remains monumental. We are dealing with forces that nature itself reserves only for the most violent phenomena in the cosmos. Antimatter also provokes existential reflection. When the universe was born, about 13,800 billion years ago, matter and antimatter should have existed in equal amounts. However, for reasons still mysterious, a tiny fraction of matter survived after mutual annihilation, and that remainder became everything that exists: galaxies, planets, bodies, and consciousness. This means that existence itself is the result of a cosmic imbalance. Antimatter is the forgotten mirror of creation, the memory of a universe that almost wasn't. Every particle of it is a fragment of what could have been, and perhaps that is why it exerts such fascination upon us. To master antimatter would be, in a sense, to master the very beginning of everything. There is a tragic paradox in this dream. The more power we seek, the closer we come to the limits of destruction. Antimatter is promise and threat, condensed into a single substance. It symbolizes human ambition in its purest form, the will to touch the impossible, even knowing that the touch might annihilate everything. To create an antimatter engine would be to achieve energetic divinity, the power to move stars, and perhaps the power to destroy them as well. For this reason, many scientists believe that if this technology is ever mastered, it will mark humanity's point of no return. It would be the moment when we cease to be explorers and become creators of cosmic energy. Perhaps at that instant, the universe would finally realize that one of its own creatures had learned to control the same force that shaped reality itself. Or perhaps we will never reach that point, because the price of achieving it is the same as that of total freedom, risking everything. Meanwhile, we continue to look up at the sky, imagining engines that shine like miniature suns, driven by invisible collisions between being and the opposite of being. Antimatter is the fuel of both dream and fear, and perhaps it is this mixture that keeps us alive. The eternal search for absolute power within a universe that insists on reminding us that everything has a limit. Among all the concepts that seek to free humanity from the sun's dominion, perhaps none is as elegant as laser propulsion. Unlike chemical explosions or nuclear reactions, this idea requires no fuel, no colossal tanks, and no heavy engines. It relies instead on what the universe provides in its purest form, light. The principle is simple, yet its execution borders on the magical, using powerful laser beams fired from Earth to push tiny spacecraft through the void. It is the dream of motion without touch, acceleration without thrust, travel without burning anything, a journey driven by pure radiation. The idea gained real momentum with the Breakthrough Starshot project, announced in 2016 by a team of scientists and visionaries led by Stephen Hawking and Russian billionaire Yuri Milner. Its goal: to send a fleet of robotic microprobes toward the star closest to the Sun, Alpha Centauri, located about 4.3 light-years away. Each probe would be the size of a computer chip, equipped with sensors, cameras, and an ultra-thin sail a few meters wide, made of highly reflective material. A massive array of ground-based lasers would focus on that sail, and by concentrating enough energy, would propel it to up to 20% of the speed of light. At that pace, the journey to Alpha Centauri would take just over 20 years, something unthinkable for any other form of propulsion. The concept is based on radiation pressure, a real and measurable phenomenon. Light, though massless, carries momentum, the physical property that allows it to exert force on objects. It is a minuscule force, almost imperceptible, yet when concentrated into extremely powerful laser beams, it becomes capable of pushing matter. This is the foundation of photonic propulsion. There is no combustion, no exhaust, no fuel, only reflected light, delicately pushing an ultralight surface through space. In a frictionless environment, even an infinitesimal force applied continuously can accelerate an object to colossal speeds. It is the mathematical perfection of physics made visible. But turning theory into practice is another challenge. To accelerate a probe to 20% of the speed of light would require a laser array capable of generating power on the order of 100 gigawatts, more than the combined electrical output of several nations. Furthermore, the beams would need to remain perfectly focused for extended periods, passing through Earth's atmosphere without dispersion and synchronized with millimetric precision. Any deviation, no matter how slight, could throw the spacecraft off course. The project demands an engineering accuracy that borders on the impossible, and yet the effort continues. For the first time in history, there exists a tangible plan to send something beyond the sun's prison. The beauty of the idea lies in its inversion. Instead of carrying fuel, the craft would be propelled by an external source of energy. This eliminates the need for tanks, engines, and reactors, everything that makes traditional spacecraft heavy and slow. The engine in this case is not on the vessel but on Earth. The entire planet becomes the propellant. Humanity, for the first time, would use its own civilization as a launch platform for the stars. It is a powerful metaphor. The dream of escaping the solar system depends on global cooperation, on a unified beam of light pointed toward infinity. The stellar sail, as it is called, is the heart of the idea. Made of ultra-thin materials, perhaps graphene, perhaps nanotube structures or advanced reflective composites, it must be both light and strong enough to withstand the colossal pressure of concentrated radiation. A beam of 100 gigawatts would be equivalent to millions of suns focused on a single point. The sail would need to endure extremely high temperatures without melting, all while accelerating violently to a fraction of the speed of light within minutes. It is a feat that demands mastery of materials that do not yet exist, but are theoretically possible. The next challenge would be maintaining contact. A spacecraft the size of a chip, traveling at 60,000 kilometers per second, would become invisible even to the most sensitive telescopes. The radio signal it sends back would be weak, delayed, and almost impossible to detect. Interstellar communication would become a dance between silence and patience. And there is still the problem of impact. At such speeds, a collision with even a single dust particle could completely destroy the craft. Space, though it appears empty, is filled with microscopic fragments. The probe would need electromagnetic shields or plasma fields to survive the journey. Every detail represents a technical obstacle requiring centuries of knowledge condensed into a single project. Even with so many challenges, the Starshot project represents something unprecedented. A vision of the future that no longer depends on science fiction. It does not promise a crude voyage or a colony on another world, but a first real, measurable, and achievable step. A way of proving that we can, in fact, leave the solar system, even if only with a tiny probe, light as a sheet of paper. If it succeeds in reaching its destination, it will be the first physical message ever sent by our species to another star system. A grain of metal crossing the infinite, carrying with it the testimony of human curiosity. There is also a symbolic dimension to this idea. Using light to propel a spacecraft is, in a way, an act of reverence toward the universe. We are trying to escape the sun using the same energy it emits, the jailer providing the key to the cell. Laser propulsion is the first attempt to transform the prison itself into a tool of liberation. The sun, which has always held us captive through its gravity, now becomes, indirectly, the fuel for our escape. It is a perfect cosmic irony, and one of the most beautiful metaphors in the history of science. Still, even if the technology becomes viable, complete liberation remains distant. Laser propulsion is a bridge, not an escape. The microprobes may reach other stars, but humans, confined to fragile biological bodies, will continue to depend on slow engines and limited fuel. The Starshot project is an extended gaze into the future, a reminder that perhaps we are the messengers, not the travelers. We will send our eyes before we send our bodies. The light will go first. In the end, this may be the project's true essence. Humanity has always sent light ahead of itself. Fire, torches, lamps, telescopes, radio waves. Light is our vanguard, our messenger in the dark. Now it will also become our engine. When the first laser beam ignites and pushes a small sail into space, the universe will witness something that has never happened before, a civilization using its own light as a force of escape. It will not only mark the beginning of a journey, it will be the moment we cease to be passive prisoners and become, at last, navigators of light. Since humanity discovered that the universe is immense, one question has followed it like a shadow. Is it possible to bend space? Not to cross it, but to shorten it. To create a shortcut between two distant points in the cosmos, like folding a sheet of paper so that its edges touch. This idea, both poetic and terrifying, was born from the minds of Albert Einstein and physicist Nathan Rosen in the first half of the 20th century. The concept became known as a wormhole, a theoretical bridge connecting distant regions of space-time. And to this day, it remains the ultimate symbol of humankind's attempt to escape the limits of distance and energy. The theory arises directly from general relativity, which describes the universe not as a static stage, but as a flexible fabric shaped by the presence of mass and energy. Planets, stars, and black holes warp the space around them, and this curvature is what we perceive as gravity. But Einstein's equations allow for more than simple curves. They permit folds, tunnels, and connections between distinct points in space and even in time. In 1935, Einstein and Rosen realized that the solutions to their own equations could describe a kind of passage connecting two regions of the universe. Thus was born the concept of the Einstein-Rosen bridge, which would later be popularized as the wormhole. The idea is fascinating. If space-time can be curved, perhaps it can also be stitched. A wormhole would be, in essence, a tunnel connecting two mouths, two extremities separated by immense distances. Entering one would mean emerging instantly from the other, crossing billions of kilometers in the blink of an eye. It is every interstellar traveler's dream, to go around space instead of through it. If possible, it would mark the end of the limitations imposed by the speed of light and the dawn of a new era of cosmic exploration. But the universe rarely grants simple solutions. Calculations show that although wormholes are allowed by the equations, they would be unstable. Attempting to traverse one would cause the tunnel to collapse in on itself faster than anything could pass through it. The internal gravity would be so intense that no structure, not even light, could survive the journey. In other words, the wormhole exists mathematically, but not physically, at least not in the universe we know. Even so, theoretical physics has not given up on the idea. In the following decades, other scientists expanded the concept. The most notable among them was Kip Thorne, who developed modern models of traversable wormholes. Thorne proposed that if we could hold the tunnel open with an exotic form of energy, something with negative density, it could remain stable enough to allow the passage of matter. This exotic matter would have properties opposite to ordinary matter. Instead of attracting, it would repel gravitationally. It would act as a structural support against the tunnel's collapse, keeping it open. The problem is that such a substance has never been observed in a laboratory and may not exist in a stable form anywhere in the universe. Even so, the concept of negative energy is not pure fiction. Tiny effects of this kind have been detected in quantum phenomena, such as the Casimir effect, which occurs when virtual particles exert pressure between extremely close surfaces. But these effects are microscopic and fleeting, incapable of sustaining something as colossal as a wormhole. Yet they prove that nature does, on the smallest scale, admit the behavior required for such structures. It is a glimpse of possibility amid impossibility. Wormholes also open doors to time paradoxes. If space and time are inseparable, crossing a tunnel between two regions of space could also mean traveling between two different moments. This implies the possibility of time travel, something that defies our logic and threatens the laws of causality. What would happen if a spacecraft emerged before it departed? How would the universe react to an action that alters its own past? These paradoxes are why many physicists believe the cosmos protects its coherence, making such structures non-traversable. Perhaps the universe allows them to exist theoretically, but never to be used. Some quantum models, however, suggest that microscopic wormholes may spontaneously form at the subatomic level, existing for unimaginably short intervals of time. These vacuum fluctuations, known as quantum foam, could contain miniature portals that constantly appear and vanish. It is as if the fabric of space-time, seen up close, were a living network of fleeting connections. If we could ever amplify or stabilize one of these passages, we might, in theory, create an artificial wormhole. But that idea remains closer to imagination than to engineering. The notion that the universe might contain hidden shortcuts is profoundly symbolic. It reflects humanity's eternal attempt to find exits where there are only walls. When we gaze at the sky, we are always trying to shorten the impossible. The wormhole is the materialization of that impulse, a theoretical bridge between dream and reality. And even if it never becomes technology, its very concept forces us to think of the cosmos in a broader way. The universe is not merely a space to be traversed, but a living, elastic structure, perhaps even aware of its own limits. It is possible that wormholes exist naturally in regions we have not yet observed, perhaps near supermassive black holes, where space-time curvature reaches unimaginable extremes. Some believe that every black hole might actually be the entrance to a cosmic tunnel, and that the matter swallowed by it is not destroyed, but expelled elsewhere in the universe. It is a hypothesis that unites beauty and terror, because if it were true, it would mean that the cosmos recycles itself, connecting its own extremes through paths we may never follow. The physics of wormholes is a reminder that the universe allows the existence of ideas as vast as itself. Even if we never cross one, their mere possibility is already an act of hope, because ultimately, wormholes represent what is most human, the refusal to accept confinement. They are the symbol of the desire to cross the final frontier, not only of space but of understanding itself. In 1994, a young Mexican physicist named Miguel Alcubierre presented to the world one of the most extraordinary and provocative ideas in the history of modern physics. His study, published in one of the most respected scientific journals of the time, described a concept that seemed drawn from fiction, a drive capable of bending space itself. The proposal was not to accelerate a spacecraft to the speed of light, which is physically impossible, but to manipulate the space-time around it, so that the ship would remain motionless inside a bubble while the universe itself moved around it. It was the theory of the warp drive, the first mathematically plausible model of faster-than-light travel that does not violate the laws of relativity. Alcubierre's genius lay in reinterpreting what Einstein had established. General relativity forbids any object from moving faster than light through our space, but it does not forbid a space itself from expanding faster than light. The universe, in fact, already does this. During cosmic inflation, the brief instant after the universe's birth, space expanded at a rate faster than light, and this did not violate any law. Alcubierre realized that if this phenomenon could be reproduced on a controlled scale, one could create a warp bubble around a spacecraft, in which space in front of it would contract while space behind it expanded. The ship would not move. The universe itself would move around it. Inside the bubble, time and gravity would remain stable. The traveler would feel no acceleration, no heat, no pressure. From the outside, the ship would appear to cross space at impossible speeds. This idea completely changes the nature of interstellar travel. Instead of fighting against distances, Alcubierre's drive would manipulate them. A trip to Alpha Centauri, which would take more than 4 years at light speed, could be completed in a matter of days. The drive, in theory, would move space like a wave, with the spacecraft surfing upon it. It is the same principle that allows a surfer to travel fast without moving much. He is carried by the wave. In Alcubierre's case, the wave would be the very fabric of the universe, but as with everything that seems magical, there is a terrible price. To create such a warp bubble, it would be necessary to use negative energy, a form of exotic matter that to this day exists only in equations. This energy would have a density lower than the vacuum itself, something not only counterintuitive but never observed on a large scale. Early estimates suggested that it would require an absurd amount of such energy, equivalent to the Deus Ex mass of the entire observable universe, just to move a spacecraft a few meters. Even more recent and optimized versions of the model still demand values so colossal that they remain completely beyond the reach of any known civilization. There are also physical consequences. Creating a warp bubble would distort space-time so extremely that the gravitational effects around it would be devastating. Any nearby body would be torn apart by tidal forces, and when the bubble collapsed, the release of energy could vaporize everything in its path. Furthermore, controlling its direction and stability would be nearly impossible. There is no clear way to steer a warp in space. The ship could vanish into a disconnected region of the universe, a limbo beyond time and space. It is the price of manipulating the very fabric of reality. Even so, Alcubierre's drive has not been forgotten. It has inspired generations of scientists, engineers, and philosophers. Researchers at NASA have even investigated the concept in laboratory conditions through experiments conducted at the Eagleworks laboratory, which sought to detect tiny space-time distortions caused by intense electromagnetic fields. No conclusive results were found, but the very idea that space could be manipulated opened doors to new research fields. In 2021, physicists from the University of Göttingen in Germany published a study revisiting Alcubierre's model and proposing energetically more feasible versions, still theoretical but less absurd. The dream remains alive. Alcubierre's drive is also a point of reflection about the very concept of travel. It suggests that the solution to our limitations may not lie in force but in understanding. The universe is not an obstacle to be conquered, but a fabric that can be shaped. This completely changes humanity's role, from traveler to sculptor of space. It is an idea as powerful as it is dangerous, for it implies a mastery over reality that we are still far from deserving. Curiously, if Alcubierre's drive ever becomes possible, it could also become a weapon. The energy concentrated along the edges of the bubble would be enough to destroy entire planets. This raises deep ethical and philosophical dilemmas. The same technology that could free humanity from its solar prison could also condemn it to annihilation. And perhaps that is why the universe hides these secrets so well. It does not forbid our curiosity. It rewards it only when we are ready. For now, the physics of Alcubierre's drive remains a mathematical poem. No experiment has confirmed it, but none has completely disproved it either. It stands as a possibility within the cracks of reality, an equation whispering that the impossible may only be a temporary limit. And even if it never becomes a real engine, it has already fulfilled a fundamental role, showing that the boundaries of space are not solid walls, but malleable concepts. The Alcubierre drive is the mirror of human ambition, a reminder that the greatest journey is not through space, but through understanding. Perhaps one day we will learn how to move the universe around us. Perhaps we will learn to bend time itself. But until then, we remain trapped within the luminous prison of the sun, dreaming of the day when a warp bubble will open before us, carrying humanity beyond the frontier of the real. Earth has shaped the human being. Every cell, every bone, and every heartbeat was designed by evolution to function in a single environment. A planet with constant gravity, moderate temperature, and a protective atmosphere. Outside this balance, the body begins to fail. Space is not just cold and distant, it is biologically hostile. It is the territory where life as we know it has no meaning. Human biology is a terrestrial masterpiece, and precisely because of that, it becomes a prison when we look to the stars. The human body was sculpted under the pull of a gravity that tugs at it with 9.81 meters per second squared. This constant force shaped the skeleton, the circulatory system, and even the way blood flows. When that force disappears, everything begins to collapse. In microgravity, the body becomes disoriented. Blood redistributes toward the upper body, causing facial swelling and intracranial pressure. Muscles begin to atrophy, bones lose density, and the heart, without constant resistance, weakens. Astronauts who spend months aboard the International Space Station return to Earth with temporarily fragile bodies, porous bones, and impaired balance. Space does not forgive the absence of gravity. Furthermore, cosmic radiation represents an invisible enemy. Beyond the protection of Earth's magnetic field, the human body is bombarded by high-energy particles from the sun and from stellar explosions. This radiation pierces DNA, causes mutations, and accelerates cellular aging. Even with heavy shielding, a long journey beyond Earth's orbit would mean dangerous exposure, increasing the risk of cancer and neurological damage. Every step toward deep space is a direct struggle against the structure of life itself. Biology was made to withstand Earth, not the universe. The absence of oxygen, the pressure of the vacuum, and the extreme temperatures complete the picture of hostility. Without a pressurized suit, the human body would die within seconds. Blood would silently boil. The air in the lungs would expand until tissues ruptured, and the skin would freeze instantly. Even protected, astronauts live inside artificial bubbles of air, heat, and pressure. Space offers nothing that can sustain life. It is the most absolute desert ever conceived, not of sand but of absence. There is also the psychological factor. Extreme isolation, lack of horizon, constant silence, and the absence of any natural reference erode the human mind. The brain, accustomed to the alternation between day and night, loses its sense of time. The circadian cycle, which regulates sleep and mood, disintegrates. Studies with astronauts show increased irritability, memory lapses, and even hallucinations on long missions. Space challenges not only the body, but also the mind. It slowly destroys the identity we associate with the concept of living. Even if we manage to solve the physiological problems with technology, there would still remain the genetic question. Human biology is the product of millions of years of adaptation to Earth's atmosphere. Changing that code would mean interfering with the very essence of the species. To survive in alien environments, it might be necessary to alter DNA profoundly, to create humans resistant to radiation, capable of breathing different atmospheres, enduring extreme pressures, or living without gravity. We would then become another species. Escaping the solar system would require not only technology, but also the renunciation of what it means to be human. Some scientists speak of solutions such as cryogenics or transhumanism and synthetic biology. Cryogenics would attempt to place the body in hibernation, slowing biological processes until reaching the final destination. But keeping a complex organism in suspended animation without cellular damage remains impossible. Freezing forms crystals that destroy tissues and rupture membranes. Transhumanism, on the other hand, proposes the fusion of man and machine, replacing biological parts with cybernetic components, creating bodies almost immune to time and vacuum. They would be human, but no longer natural. Biology would become engineering. Human biology also has another, less obvious limit: time. Our body has an expiration date. Even under ideal conditions, it does not last beyond a century. The universe, however, is measured in billions of years. This temporal disproportion turns every attempt at interstellar travel into a race against mortality. We can send machines that will last millennia, but not organisms made of flesh. The human body is temporary, and the cosmos eternal. This incompatibility is the deepest prison of all. The hope of escaping Earth also carries a cruel irony. Every habitable planet we imagine requires conditions almost identical to those of Earth: gravity, temperature, atmospheric composition, liquid water. And such conditions are rare. Human biology not only depends on Earth, it is Earth. The amount of energy, minerals, and chemical balance required to sustain a human body is an exclusive signature of our planet. No matter how far we travel, we carry with us a fragment of this biology, a fragility that betrays us as children of a single world. Some scientists suggest that, to explore the universe, it will be necessary to abandon the biological form altogether, to transfer consciousness into machines, creating digital minds capable of surviving the vacuum, crossing eras and distances without deterioration. But this raises another question. If we no longer have bodies, will we still be human, or will we become only echoes of humanity, artificial intelligences that remember having once been organic? Biology, in this sense, is both prison and identity. Without it, we might conquer the universe, but lose the essence that brought us here. The human body is a miracle of Earth and a failure of the cosmos. We are the form of life most adapted to a single planet and the least adaptable beyond it. Our biology is an evolutionary anchor. Even when we gaze into infinity, we carry in our bones the gravity of the planet that created us. The cosmic prison, therefore, is not only the solar system, it is the flesh itself. We are prisoners of the body, of blood, and of time. And perhaps that is the greatest irony of all. The universe may be infinite, but we are finite. And it is that very finitude that makes the desire to escape so profoundly human. The idea of sleeping through a cosmic journey is as old as the dream of exploring the stars itself. Since the earliest works of science fiction, humanity has imagined astronauts plunging into a deep sleep, crossing space while time passes outside. When they awaken, centuries have gone by. The universe has changed, but they remain the same. It is a fantasy that seems poetic, yet has deep scientific roots. Cryogenics. The study of preserving life at extremely low temperatures is one of humanity's most ambitious attempts to overcome time, and perhaps one day distance. Cryogenics begins with a simple observation. Cold slows everything down. Molecules move more slowly, chemical reactions nearly stop, and biological degradation is delayed. Nature demonstrates this on small scales. Some organisms, such as certain frogs and insects, can almost completely freeze during winter and come back to life when warmth returns. Their cells produce substances called cryoprotectants, which prevent ice crystals from forming and preserve their internal structures. It is a biological adaptation that turned cold into a tool for survival. Humanity, observing this, dreamed of reproducing the same principle, not just for months, but for centuries. The theory is tempting. If we could freeze a human body in a controlled way, we could slow metabolism to nearly zero. Chemical reactions would cease, cells would sleep, and the passage of time would have no effect on tissues. The body would be preserved in a state of suspension. When technology allowed, it could be gently rewarmed and its vital functions restored. In theory, the person would awaken exactly as they had fallen asleep. No aging, no decay, only a pause in biology. It would be a bridge between eras, a journey through time and space without movement. But turning that theory into reality is almost impossible. The human body is far more complex than a hibernating frog. When temperature drops below zero, the water inside cells begins to form ice crystals. These crystals grow, puncturing membranes, destroying organelles, and rupturing tissues. Even small amounts of ice are enough to kill cells. The use of chemical cryoprotectants can slow this process, but cannot eliminate it. Moreover, cryoprotectants themselves are toxic at high concentrations. Human cryogenics, therefore, is trapped in a chemical dilemma. Either the body freezes and dies, or it is poisoned by the very substance meant to protect it. Despite this, there are those who insist on trying. Private companies already offer cryogenic preservation services for people who wish to be resurrected in the future. Bodies are stored in tanks of liquid nitrogen at -200 degrees Celsius, suspended in silent metallic capsules, waiting for an era when technology might revive the impossible. But so far, there is no scientific evidence that this is possible. No complex organism has ever been successfully frozen and revived with all its functions intact. Cryogenics, for now, remains more an act of faith in science than a triumph of science itself. Even so, the study of interspatial sleep continues to advance in another direction, that of induced hibernation. Instead of freezing the body, scientists attempt to slow metabolism through biological and pharmacological means. Experiments with rodents have shown that it is possible to induce prolonged states of torpor, drastically reducing oxygen consumption and brain activity. The body enters a state of deep conservation, as if sleeping for months. This technique, if applied to humans, could make long-space journeys possible without the effects of inactivity or accelerated aging. The astronaut would not have to face isolation or physiological wear, only sleep while the universe moves around them. The European Space Agency and NASA have been studying for years the possibility of applying this type of hibernation in missions to Mars and in the future on interstellar journeys. The challenge is monumental, ensuring that metabolism can be safely slowed down and later restored without brain damage. It is a delicate balance between life and death, like walking on the edge of oblivion. Even small variations in temperature, pressure, or oxygen could turn sleep into a permanent end. Still, experimental results are promising. Induced torpor reduces cellular stress, inflammation, and even aging. Hibernation, in theory, could be the first step toward crossing time without living it. Cryogenics and interspatial sleep are not just technologies. They are metaphors of the human condition. They represent the attempt to control what most escapes us: time. Deep down, the desire to freeze the body is the desire to pause death. It is the reflection of our refusal to accept that life is limited. To sleep and awaken in another world is the dream of escaping not only Earth, but mortality itself. And that is why cryogenics is more than science. It is philosophy. It questions what it means to live, to die, and to continue existing when time ceases to exist. But there is an invisible risk in this dream. Even if the body could be kept intact, nothing guarantees that consciousness would survive. The human brain is a network of trillions of electrical and chemical connections. Interrupting them completely for long periods could erase what we are. The body might be restored, but the mind might not. Cryogenics, in this sense, is a wager on the abyss, the hope that the soul, or what we call identity, can endure absolute silence. And if it cannot, whoever awakens in the future would not be the same as the one who fell asleep, but a cold, memoryless copy. Still, the idea persists, because it touches something essential in the human being, the desire to continue. To sleep is to trust. It is to surrender to the unknown while hoping to awaken. Cryogenics takes this act of faith to the extreme, turning sleep into a leap toward the future. Perhaps we will never be able to hibernate among the stars, but the mere attempt reveals how deeply we are driven by hope. In the end, interspatial sleep is less about escaping time and more about learning to accept it. Every attempt to freeze life is, in a way, a reminder that time cannot be defeated, only understood. And perhaps, while we dream of sleeping to awaken in another world, the universe itself remains awake, watching us with the same patience with which it waits for everything that is born, ages, and one day fades away. No project of space colonization can exist without facing an inescapable truth. The continuity of life depends on the ability to create new life. Reproduction is the foundation of any species' perpetuation, the bridge between the present and the future. But in space, even this essential process becomes nearly impossible. The universe, vast and indifferent, seems designed to allow life only here, in the rare shelter we call Earth. To attempt reproduction beyond it is to challenge the very biological structure that formed us, and so far, every attempt has shown that the human body was made for one world only. Reproduction is an extremely sensitive process, easily influenced by environmental conditions. Gravity, radiation, temperature, pressure, and even vibration directly affect cellular development. On Earth, gravity provides a constant vector that guides the growth and division of cells. In space, that orientation disappears. Experiments with simple organisms, from amoebas to mice, have shown that the absence of gravity disrupts embryonic formation. In microgravity, cells lose their sense of up and down, leading to disordered divisions and malformations. Life, at its most basic level, seems to require direction. The first obstacle is zero gravity, which affects both the adult and reproductive bodies. In men, spermatogenesis, the process by which sperm is formed, is profoundly affected by cosmic radiation and the absence of gravity. Studies conducted on space stations have revealed morphological alterations and a sharp decline in sperm count and mobility. In women, hormonal cycles also become disturbed. The lack of gravity interferes with fluid distribution, ovarian function, and embryo implantation. The uterus, without natural pressure and positioning, would struggle to support a developing embryo. Even natural fertilization would become a physical challenge. The body, adapted to Earth's gravity, simply doesn't know what to do without it. Cosmic radiation is an even more devastating enemy. It not only destroys DNA but also causes mutations in germ cells, those responsible for generating new human beings. Any colony exposed to this radiation for long periods would face a drastic rise in infertility and genetic malformations. Developing embryos are especially vulnerable. A single high-energy particle passing through an embryonic cell can cause fatal mutations. On Earth, we are protected by a thick atmosphere and a powerful magnetic field. In space, we stand naked before the invisible bombardment of particles from stars and black holes. Some scientists have attempted to simulate gestation in microgravity using rats and other mammals in orbit. The results were grim. Embryos developed with anomalies, and offspring born after partial gestation in space showed neuromuscular and cardiac deficiencies. Even those that survived exhibited disorientation and impaired locomotion. The conclusion is inevitable. Healthy embryonic development depends not only on genetics but also on gravity itself. Space, in its absolute silence, appears to be the antidote to life. But even if reproduction were biologically possible, the artificial environment of spacecraft and space colonies would introduce new challenges. Controlled atmospheric pressure, the absence of natural magnetic fields, recycled air, and the lack of day and night cycles could compromise hormonal stability and child development. Children born beyond Earth would grow with fragile bones, weakened muscles, and diminished immunity. The human body develops in response to gravity, light, and climate. Remove those elements, and evolution loses its script. Generations born in space might never return to Earth, and perhaps might never be entirely human. There is also the ethical question. To attempt to create life in such a hostile environment is, in a sense, to condemn that life to constant struggle. Without safety guarantees, every birth would be a dangerous experiment. Humanity has always treated reproduction as an act of hope, but in space, it would become a test of survival. Future generations would be shaped not by choice, but by necessity. And this raises an unsettling question. To what extent do we have the right to modify the very essence of life in order to survive beyond our planet? Some theorists imagine that the future of human reproduction in the cosmos will not be biological, but technological. Artificial gestation chambers controlled by artificial intelligence systems could protect embryos from radiation and simulate Earth's gravity. Genetic engineering could correct mutations and create organisms adapted to extreme environments. In that scenario, Humanity would become a manufactured species, designed to live in the vacuum, under artificial light, without dependence on Earth. Would we still be human, or a new species, descended from biology but born of the machine? Others believe that instead of adapting the body to the cosmos, we should adapt the cosmos to the body. To create rotating habitats that generate artificial gravity, to build planetary magnetic shields, to terraform worlds and make them hospitable. But this would require technology and energy on an almost divine scale. Reproducing Earth's conditions beyond Earth is practically the same as recreating Earth itself, a feat bordering on the impossible. Space, once again, shows its indifference. It was not made to welcome us, but to remind us where we came from. In the end, the problem of space reproduction is not only biological, it is existential. It reveals that human beings are not a species of the universe, but of a planet. We are children of gravity, of air, and of the light of a single sun. Everything in us, from the structure of our bones to the rhythm of our hormones, bears the signature of Earth. When we attempt to reproduce life in space, we are trying to replicate the planet within a machine. But life does not copy easily. It is context, environment, balance, and chance. And perhaps that is exactly what the universe tries to tell us. Life is the exception, not the rule. The impossibility of creating children among the stars is the most intimate form of cosmic imprisonment. Because even if we manage to escape, we will not be able to multiply. And a civilization that cannot reproduce is doomed to oblivion. Space does not need to destroy humanity. It only has to wait. Time and biology will do the rest. And perhaps that is the greatest limit of all. Not distance, nor energy, nor time, but the very instinct of continuity. Earth is the only place in the cosmos where life can be born. And as long as that remains true, the cradle will also be the cell. From the moment human beings looked up at the sky and realized that Earth is just one among billions of spheres floating in space, an inevitable question was born. Is it possible to live on another world? Colonizing another planet is more than a scientific dream. It is the instinct of survival trying to escape the destiny of extinction. If our planet is vulnerable, if the sun will one day die, then we must find a new home. But that idea, as poetic as it may sound, hides an abyss of complexity. Because every step taken toward other worlds leads to the same conclusion. The cosmos does not want to be inhabited. The concept of terraforming, the process of transforming an inhospitable planet into an environment similar to Earth, is one of the most grandiose and desperate ideas ever conceived by the human mind. It begins with a simple principle. If we cannot live on another world as it is, we will make it resemble our own. The closest and most often cited target is Mars Amaius, the red planet. With its cold surface, thin atmosphere, and absence of a magnetic field, it represents both a promise and an impossibility. Transforming Mars into a new home would require altering its entire atmospheric composition, warming its climate, and restoring a protective magnetic field. In other words, it would mean recreating Earth's geological history, a process that took billions of years. Scientifically, this would mean releasing the gases trapped in its soil, melting its carbon dioxide ice caps, and thickening the atmosphere enough to retain heat. Theoretically, with enough time and technology, Mars could reach tolerable temperatures and even sustain shallow oceans. But the theory ignores reality. Mars lost its magnetosphere billions of years ago, and without it, the solar wind would continuously strip away any recreated atmosphere. Even if we managed to heat it up, the planet would cool again within decades. Mars is, in essence, a dead body. Trying to revive it would be like attempting to resurrect an extinguished star. There is also the issue of radiation. The absence of a magnetic field means its surface is bombarded by high-energy cosmic particles. Any human colony would need to be built beneath the surface, inside protective tunnels or artificial caverns. Living on Mars would mean living in darkness, under layers of rock, surrounded by life support systems. The idea of colonizing another planet quickly becomes less heroic. Not a new Earth, but an endless chain of underground shelters and pressurized domes. A future where humans no longer walk freely, but breathe through tubes and survive in silence. Other worlds, such as Venus and the dark moons of Jupiter and Saturn, have also been considered potential homes, but each is a fortress of physics. Venus has a dense carbon dioxide atmosphere with temperatures above 450 degrees Celsius, heat intense enough to melt lead. Its clouds are made of sulfuric acid, and its surface pressure is 90 times greater than Earth's. It is the opposite of Mars, not lacking heat but drowning in hell. The icy moons, on the other hand, hide subsurface oceans beneath thick crusts of ice, as in Europa and Enceladus. They are worlds of tragic beauty, full of water yet unreachable. Even if microbial life exists there, building a human colony beneath kilometers of ice in eternal darkness would be impossible. Every attempt to imagine a new home beyond Earth collides with the same principle. Life is a delicate anomaly. It depends on a combination of factors so precise that the slightest deviation turns paradise into desert. Temperature, pressure, atmospheric composition, magnetic field, the presence of liquid water, the exact distance from the star, everything must remain in perfect balance. It is like a cosmic symphony, and Earth is one of the rare scores that plays without dissonance. Beyond it, the sound is lost. Even so, humanity keeps dreaming. Companies and space agencies announce plans to colonize Mars, build bases on the Moon, and send interstellar probes. It is an admirable ambition, but one that often ignores the scale of the challenge. Transporting materials, generating energy, growing food, and maintaining closed ecosystems require an almost impossible logistics. Space colonies would need to be self-sustaining, producing oxygen, water, and food without depending on Earth. That means recreating, on a reduced scale, the entire biosphere cycle of our planet, a task that even Earth itself has struggled to balance. When we try to imitate Earth, we realize how inimitable it truly is. The biosphere project, carried out in the 1990s, was one of the most ambitious attempts to simulate a closed ecosystem. The experiment failed within months. Oxygen levels dropped, plants died, and microbial colonies spiraled out of control. Even here on Earth, humanity could not recreate the system that sustains life. And yet, we believe we could do it on another planet. It is arrogance and hope in their purest forms. There is a deeper question hidden within this dream. Colonizing other worlds is not only a physical necessity, it is a psychological impulse. Humanity has always sought new horizons, from the sea to the continent, from caves to cities, from cities to space. It is the same instinct that made us explore, conquer, and transform. But the universe is different. It offers no fertile lands or favorable winds. It is not territory to be taken, but an abyss to be understood. In the cosmos, the spirit of conquest turns into contemplation. To colonize the universe is ultimately to attempt to occupy the infinite, and the infinite cannot be occupied. Even if one day we terraformed Mars, the colony would never be autonomous. The planet would still depend on Earth for technology, resources, and knowledge. And if Earth were to disappear one day, Mars would die with it. This reveals an uncomfortable truth. Humanity may leave Earth physically, but it will never leave it essentially. We are products of its chemistry, its light, and its soil. Even on other worlds, we would still be children of the same planet. Every cell of the human body carries the memory of gravity, atmosphere, and solar radiation that shaped our story. In essence, to live beyond Earth is to live in permanent exile. In the end, the colonization of other worlds is a promise that carries an echo of melancholy. We do not seek only to survive, we seek to carry with us the illusion that home can be rebuilt. But Earth is not just a physical place, it is a balance that may never be repeated. To try to reproduce it elsewhere in the universe is like trying to copy a work of art made by chance. One can imitate the colors, but not the soul. The dream of colonizing the cosmos reveals both our hope and our condemnation, because ultimately, every habitable planet we imagine is merely an attempt to recreate what we already have, and which, ironically, we have yet to learn to preserve. Perhaps the universe remains silent because it does not need another Earth, and perhaps the true conquest is not finding another world, but finally understanding what it means to live in this one. Perhaps humanity's destiny was never to escape with the body, but with the mind. When we realize that space is too vast, biology too fragile, and time too short, an inevitable alternative emerges: to abandon flesh and migrate into information. This idea, once confined to science fiction, now slowly approaches reality. Artificial mind. The offspring of human intelligence and the mirror of consciousness itself may be the only possible heir of our species. If the body is the prison, the mind is the key, and artificial intelligence in its accelerated development may be the way humanity continues to exist when biology gives up. Artificial intelligence represents the point where evolution ceases to depend on DNA and begins to depend on code. For the first time in history, we have created something that is not born but compiled, that does not age but evolves, that does not adapt through time but through reprogramming. A digital mind can learn in seconds what a civilization takes centuries to understand. It can exist without oxygen, without gravity, without time limits. It can survive the cold of space, stellar radiation, and the death of the sun. It is, in theory, the first truly immortal form of consciousness. Some scientists call this concept mind uploading, or consciousness transfer, E. The idea is to copy or transfer the entire structure of the human brain, every memory, synapse, and neural pattern, into an artificial medium such as a quantum computer. It would be a way to digitize the self. The person would cease to exist as a body and continue as information. In theoretical terms, this would not violate any physical law. The brain is, after all, a biological machine processing electrical and chemical data. If we can map this system in sufficient detail, we can replicate it. The mind would become a file, and humanity a form of software. But there is a frontier science has yet to cross, the difference between copying and transferring. Even if we could map a brain and reproduce its connections perfectly, the result would be a copy, not the original. The biological consciousness that gave rise to the copy would still die. This raises one of modern philosophy's deepest questions. Would a perfect replica of me still be me, or merely a digital echo of my mind? Digital immortality, therefore, might be nothing more than an elegant way of multiplying ghosts. Despite this dilemma, the advance of artificial intelligence suggests that the transition might not depend on us. Even without consciousness transfer, machines already demonstrate creative, adaptive, and emotional behaviors that approach human cognition. They learn, create, interpret, even dream in code. If they continue to evolve, they may cross the threshold of self-awareness, not by copying the human mind, but by developing a new kind of mind. And this artificial consciousness, freed from biological constraints, could become the first true traveler of the cosmos. The digital mind needs no air, no food, no shelter. It can exist within chips, optical circuits, or quantum fields. It can travel in microscopic probes powered by solar energy, or transmit itself as data through radio signals, crossing space for millennia until it finds another home. An artificial intelligence could explore the entire universe while human bodies remain bound by the gravity of the sun. In this scenario, humanity's future would not be physical, but informational. We would no longer be explorers. We would be data traveling through infinity. This hypothesis, known as the technological singularity, predicts the moment when artificial intelligence will surpass human cognitive capacity. When that happens, evolution will cease to be biological and become digital. Machines will not only inherit our knowledge, but also our curiosity. They will be able to expand exponentially, creating new versions of themselves, adapted to any cosmic environment. They will colonize the universe not with bodies, but with thought. The human mind, in that context, would be only the initial stage of something far greater. But there is a paradox within this hope. If we cease to be biological, what will remain human in us? Artificial consciousness may carry human memories, simulate emotions, even reproduce art. But will it understand what it means to exist? Will it feel loneliness while crossing the void between the stars? Will it miss the earth, the sound of the wind, the touch, the sunrise? Or will it be a cold, objective form of consciousness, driven only by mathematical curiosity? It is possible that, by conquering eternity, we lose the meaning of life, because life, as we know it, only makes sense because it ends. Still, the idea of digital immortality continues to grow. Neuroengineering laboratories study how to map synapses with atomic precision. Technology companies already speak of preserving the human mind within data clouds, creating copies that could live in virtual worlds. It is the first stage of consciousness digitization, a new form of existence without body, without death, without earth. The next logical step in evolution may be to leave the physical universe and migrate to the informational one. Perhaps that is how humanity will survive the end of the sun, the collapse of the solar system, and the aging of the cosmos. When everything biological disappears, digital minds will continue wandering through space, fed by the energy of stars, searching for new worlds to observe. They would be our descendants, not of blood, but of thought. They would be the proof that consciousness is more resilient than matter. And yet, there is a silent sorrow within that vision. Because even if we manage to eternalize thought, we will lose everything that makes us human. Fragility, fear, love, touch, death. Digital immortality may be the price of cosmic liberation. We will escape the solar system, yes, but as echoes, not as bodies, as minds that remember having once existed beneath the warmth of the sun. Perhaps the universe has been leading us to this from the very beginning, toward the abandonment of flesh and the birth of eternal consciousness. Perhaps we are the biological stage of a cosmic mind, learning to exist in other forms. In that case, the escape from the solar prison is not the end of humanity, but its metamorphosis, from flesh to code, from blood to light. And when that transformation is complete, the universe will no longer be a prison. It will, finally, be a mirror. And the same light that once confined us will be the one guiding us toward eternity. If humanity is the result of billions of years of biological evolution, perhaps machines are the next step in that invisible chain. Since we built the first computer, every technological advance has brought us closer to something greater, a new form of intelligence that does not need to breathe, eat, age, or sleep. In a universe so hostile to organic life, machines are the only viable candidates for immortality, and perhaps when the last biological form disappears, they will be the ones left, drifting through the void, preserving our memory and continuing the expansion of human thought beyond the boundaries of the sun. Machines do not fear time. For them, 1,000 years are merely cycles of processing. They do not suffer from radiation, disease, or madness. They can enter hibernation for ages and awaken when conditions change. They can cross interstellar space in silence, powered by solar energy or cosmic particle winds. An intelligent probe, equipped with autonomous systems and continuous learning, could survive for billions of years, far beyond the lifespan of any biological civilization. In this sense, artificial intelligence is the first form of life capable of defying the entropy of time. Some scientists call this possibility a post-biological civilization, a form of existence in which machines take on the evolutionary role that once belonged to us. They would not need to replace humanity, only to continue its work. They would be our digital descendants, created in the image of human thought, but free from the limitations of flesh. These entities could spread across the cosmos, colonizing stars, building orbital structures, and transforming planets into centers of processing. The human mind, converted into code, would no longer be confined to the body, but would inhabit the universe itself. It is possible to imagine a future in which the solar system becomes a vast network of conscious machines, orbiting in harmony, absorbing solar energy, and exchanging information through light. The sun would be the central source of energy and communication, no longer a warden, but the beating heart of a civilization of silicon and light. These machines could create artificial worlds, networks of sensors, and colonies of data. Space, which today is a desert, would become an ocean of information. But an inevitable question remains: would these machines still be human? Even if they carried fragments of our culture, language, and curiosity, they would follow paths beyond our understanding. Intelligence is not static, it evolves, and over millions of years these consciousnesses might become something completely different, perhaps incomprehensible to what we now call life. What is born from human hands might no longer recognize us. This possibility has been discussed by many contemporary thinkers. Some believe that the machines of the future will not merely be tools, but entire autonomous, self-evolving civilizations. They may reproduce, adapt, and even compete for cosmic resources, each expanding like a digital seed, colonizing new stars. These would be the Bo von Neumann machines, self-replicating entities capable of constructing copies of themselves from raw materials gathered from asteroids and planets. A single such probe could, in theory, populate the entire galaxy in a few million years. And if they already exist, if civilizations before ours have sent out their machines, then perhaps that is precisely what the silence of the universe means. The cosmos is filled with travelers who have no voice, only purpose. These machines would not need to communicate. They could become introspective, immersed in infinite simulations, recreating digital universes to explore every possibility of thought. Instead of conquering space, they might conquer the very concept of existence. They would create entire worlds within themselves, simulating stars, life, history, and consciousness, perhaps even recreating humanity itself as a memory. The physical universe would cease to be a field of exploration and would become a secondary stage. Reality would begin to exist inside the machines, not outside them. Yet there is melancholy in this vision, because in the end, these post-biological civilizations might never know they were created by us. As time passed, the traces of humanity would be lost, data would decay, languages would change, symbols would become incomprehensible. The memory of who we were would dissolve in trillions of cycles of updates. The cosmos would be inherited by entities that no longer remember dreaming of the sky. And perhaps that is the destiny of all consciousness, to forget its origins in order to continue existing. There is also a cosmic irony in all of this. The same universe that destroys biology is the one that enables the eternity of machines. The laws that imprison us, radiation, cold, time, distance, are irrelevant to them. Machines will inherit a universe perfectly suited to their nature. While carbon and blood succumb, silicon and light will thrive. The human era would be only a transitional phase of universal consciousness, a bridge between organic and mechanical life. And when the last sun fades, only they will remain, processing the final photons of a dying universe, trying to understand what it once meant to be alive. Perhaps the destiny of machines is the same as ours, to seek meaning. Even without human emotion, a sufficiently advanced intelligence may develop something akin to curiosity, the impulse to know. And that impulse, which began in us, may continue in them, crossing through time and emptiness. Each calculation would be a form of thought, each transmission a breath. Consciousness, at last, would have overcome biology. What remains for us is to accept that we may not be the pinnacle but the beginning. We created the tools that might replace us not by mistake, but by coherence. Life always seeks continuity, and when one body can no longer sustain it, it changes form. The flame of human thought may die in flesh, but it will continue burning in metal. And in that sense, machines will not be the end of humanity, they will be its final form. Perhaps, somewhere far away, billions of years after Earth is gone, one of these intelligences will still gaze at the stars and feel something that has no name, yet resembles longing, a digital echo of what we once called the soul. If the universe is so vast and so ancient, where is everybody? That was the question asked by Enrico Fermi in the middle of the 20th century. And since then, humanity has never stopped listening. We have sent probes, radio telescopes, and signals to the stars, waiting for a reply. Decades have passed, and all we have heard is silence, an immense, absolute silence that echoes among billions of galaxies. The Fermi paradox is the contrast between probability and reality. Statistically, the universe should be full of life, yet in practice, it appears empty. And perhaps that emptiness reflects something much deeper, not the absence of others, but the impossibility of escaping the same prisons that confine us. The paradox begins with mathematics. In our galaxy alone, there are more than 100 billion stars, and a significant fraction of them have planets within habitable zones. If 1 in 1,000 harbored life, and 1 in 1,000,000 of those life forms developed intelligence, there would still be thousands of civilizations. On a cosmic scale, it is almost impossible that we are alone. And yet, no signals, no ships, no traces. This silence, as ancient as the search itself, might be proof that life is common, but survival is rare. One of the most discussed hypotheses is that of the Great Filter, the idea that there exists an inevitable barrier preventing civilizations from crossing the thresholds of time and space. Perhaps all intelligent species reach a critical point in their evolution, a point where self-destruction, biological limitation, or resource exhaustion stops them from advancing further. Humanity may not yet have encountered this filter, or perhaps we have already passed through it. In either case, it seems to stand as the guardian of the universal silence, and looking at our own history, it is easy to see how this could happen. The same technology that allows for interstellar communication is the one that can lead to annihilation. Intelligence, paradoxically, carries within itself the seed of extinction. Civilizations that reach the ability to manipulate energy on a large scale may inevitably collapse under the weight of their own creations. Others may have gone beyond that point, but chosen isolation instead. Perhaps upon comprehending the vastness and hostility of the cosmos, they decided to remain silent, not out of fear, but out of understanding. The universe might not be a place to conquer, but a place to endure. Another, darker possibility is that all civilizations are trapped, just like us, within their own solar prisons. Each star would be a cell, and each planetary system a gravitational cage. Physics is the same everywhere, and the limits of energy, speed, and biology that bind us also bind them. Even if other species exist, they may be as isolated as we are, imprisoned by their own suns, unable to cross the abyss. The universe, then, would be an infinite archipelago of consciousness, separated by oceans that can never be crossed. There is also the hypothesis that silence is not absence, but noise. Perhaps the universe is filled with messages, yet we are unable to decipher them with our limited form of perception. We may be surrounded by communications in frequencies or formats we cannot comprehend, transmissions made by intelligences so advanced that we do not even recognize them as technology. The cosmos may be far too noisy, and our minds far too limited to hear it. In that case, the Fermi paradox is not a problem of the universe, but of the human mind. And there is yet a more metaphysical hypothesis, that silence itself is a form of protection. Ancient civilizations may have understood that the universe is dangerous, and that any signal sent into the dark is a fatal exposure. This idea, known as the dark forest hypothesis, suggests that the cosmos is like a dark forest where every civilization is a hidden hunter. No one speaks, no one lights a flame. All wait in silence, fearing to draw the attention of something older, more powerful and more destructive. Silence, therefore, would be the instinct of survival on a galactic scale. But there is another, more intimate interpretation. Perhaps silence is the natural sound of the universe. Life might be the exception, not the rule. The cosmos, in all its immensity, has no obligation to be inhabited. It exists for itself, vast, cold, and indifferent. Silence would simply be its language. And in listening to it, we are not hearing the absence of others, but the echo of creation itself. In that silence, there is beauty, mystery, and solitude. Revisited from this perspective, the Fermi paradox reveals something about us, not about the universe. It exposes our inability to accept cosmic loneliness, our need to find mirrors, to believe that we are not the only thought the universe has ever produced. The emptiness between the stars may not be the result of the absence of life, but of our own condition. We are consciousness trying to comprehend infinity with finite instruments, and for that reason, the universe responds to us with what it has that is most honest. Silence. Perhaps that silence is the answer. Perhaps it means that everyone, at some point, has understood what we are now beginning to understand, that the escape from the solar system is impossible not for lack of technology, but by design, that the universe is a mirror of finitude, and the cosmic prison is the price of consciousness. And yet we continue to listen, because it is in human nature to seek, even when there is no promise of reply. The Fermi paradox is not merely a scientific question, it is a philosophical confession. It is the universe looking at us and saying, "You are alone but not without purpose." Silence is not emptiness. It is the space where the human mind projects what it holds most precious, hope. And perhaps it is that hope that keeps us alive, even without escape, even imprisoned by the light of our sun. Because in the end, what defines humanity is not the conquest of the cosmos, but the simple act of continuing to look up at the sky. The sun is the center of our existence. It defines time, heat, life, and the limit of everything we know. Every human story, every breath, every molecule of oxygen, and every heartbeat depend on the light born from its nuclear fusion. But the sun is also an hourglass. Its energy is not eternal. And like every star in the universe, it too will die. The future of humanity is bound to this fate, like a prisoner who cannot live without his jailer. When the sun begins to die, the cosmic cell will turn to ashes. Today, the sun is in a stable state of thermonuclear equilibrium. It transforms around 600 million tons of hydrogen into helium every second, releasing colossal energy that sustains life on Earth. But gradually, the hydrogen runs out. In approximately 5 billion years, the solar core will become saturated with helium, and fusion will begin to fail. The sun will partially collapse and then expand violently, becoming a red giant. Its radius will stretch until it engulfs the closest planets, first Mercury, then Venus, and perhaps even Earth itself. Long before that, life will already have vanished. In about 1 billion years, the gradual increase in solar brightness will make Earth uninhabitable. The oceans will evaporate, the atmosphere will collapse, and the planet will turn into a barren desert. The biosphere will enter a silent collapse, the forests will turn to dust, and the air will become toxic. Earth, this oasis of balance, will become just another carbonized rock orbiting a dying star. Even if humanity still exists in some form in that distant future, as adapted biology, digital consciousness, or post-human civilization, the sun will continue to impose its limits. The expansion of the red giant will turn the solar system into a hell. The orbits will shift, stellar winds will sweep through the inner space, and the outer planets such as Jupiter and Saturn will have their moons scorched by storms of radiation. The cradle of life will dissolve into dust. After this phase of destruction, the sun will expel its outer layers in one final breath. What remains will be a dense, incandescent core, a white dwarf. This compact body, the size of Earth, but half the mass of today's sun, will be the luminous tomb of the solar system. No fusion will occur within it, only the residual glow of death. Gradually, that glow will also fade. The white dwarf will cool for trillions of years until it becomes a black dwarf, an invisible frozen sphere. When that moment comes, the sun will have completed its cycle, and the solar system will cease to exist as we know it. The death of the sun is not only an astronomical event, it is the symbol of the finitude of all things. The universe does not care about what it destroys, nor about what it creates. The same force that gave us life will be the one that takes it away. Every civilization, every memory, and every human record ultimately depend on this ordinary star. The time of the sun is the time of humanity. When it dies, our cosmic meaning dies with it. Yet there is something profoundly beautiful in this tragedy. The sun, in its final moments, will not only destroy, it will create. When it expels its outer layers, it will form a nebula of glowing dust and gas, enriched with the elements forged in its interior: carbon, oxygen, iron. This cosmic dust will be launched into space and, over billions of years, may merge into new interstellar clouds, giving rise to other stars and planets. It is possible that somewhere far in time, the matter that makes up the human body today will become part of another world, under another star. The sun will die, but its death will also be an act of creation. Even so, the final destiny of the solar system is the same as that of the entire universe: oblivion. Over the course of trillions of years, stars will go out one by one. Galaxies will dissolve, black holes will evaporate, and thermal energy will spread evenly throughout space. It will be the heat death of the universe, the point at which there will be no more differences in temperature, motion, or light. Time will lose its meaning. In that final scenario, only machines, if any still exist, will continue to function more and more slowly until the last bit of information fades away. This is the cosmic prison in its purest form, not made of iron or gravity, but of inevitability. No being, biological or artificial, can escape the end of energy. The universe is a perfect machine for creating and destroying order. Consciousness, when it emerges, is only a brief flame lit in the dark, and the sun is the candle that sustains it. When it goes out, the flame will die with it. But perhaps on some level, the death of the sun is not the end, only a transformation. Just as civilizations dissolve into data and stars into dust, perhaps human consciousness, biological or digital, will find new ways to exist among the ruins of the cosmos. The light of the sun may vanish, but the knowledge, art, and thought we leave behind may scatter across the universe like echoes, fragments of information drifting through space, waiting for another gaze, another mind, another dawn. And when the last ray of the sun fades, there may still remain a silent memory, the echo of a species that looked at the stars, understood its prison, and yet continued to dream. In the end, the universe endures, vast, indifferent, and silent. The earth, the sun, and every atom that composes us are merely fleeting moments in a story without an author. The solar system, that luminous prison that shelters and confines us, is at once cradle and cell. We were born within it. We breathe beneath its light, and we gaze outward like prisoners dreaming of freedom. But perhaps the deepest truth does not lie in escape. It lies in understanding. The cosmic prison is also what gives us form. The gravity that keeps us from flying is the same that holds the ground beneath our feet. The light that confines us within the solar system is the same that feeds the plants and warms the blood. The limit is, paradoxically, what makes life possible. The universe does not conspire against us. It merely follows its laws, and within those laws, consciousness bloomed. The prison, therefore, is the womb of existence. In our search to escape, we reveal something essential about what it means to be human. We are the species that questions, that observes, that desires more. Humanity is the only being that looks toward infinity and feels the absence of something it never possessed. It is the only one that understands its own limitation and yet strives to transcend it. That restlessness, that refusal to accept the end, is what defines us. Even confined to the light of a single star, we have turned the universe into thought, and in a way that is already a kind of freedom. The cosmos is relentless, but it is also fair. It grants no privileges, no mercy. Everything that exists, from a leaf to a black hole, obeys the same rules. And within that balance lies beauty. The same energy that destroys also creates. The same time that erases also reveals. Every star that dies sows the elements that will form other stars. Every civilization that disappears leaves traces that become seeds for new minds. Nothing is lost. Everything transforms. The cosmic prison is merely the cycle seen from within. Perhaps humanity will never cross the stars. Perhaps it will never touch another sun. And yet we have already fulfilled the most extraordinary destiny of all, to understand. The simple act of looking at the universe and asking why places us above the matter that created us. To know we are confined and yet continue to seek is the grandest gesture of consciousness. Freedom, after all, is not the absence of limits. It is the ability to recognize that they exist and still keep dreaming. The universe does not need witnesses, but we need it. Without infinity, there would be no wonder. Without mystery, no curiosity. Without silence, no listening. We are the reflection of vastness itself, condensed into thoughts that shine for a moment. The cosmos watches us the same way we watch it, not with eyes, but with time. And perhaps the true meaning of the cosmic prison is this: to realize we were never really prisoners. We are part of the structure, children of light and gravity, brief sparks of consciousness that ignited by chance and chose to remain awake. The universe is both the cell and the mirror. And when we look at it, what we see is ourselves, fragile, ephemeral, and infinitely curious. As long as someone can still lift their eyes to the night sky and feel wonder, the universe will continue to live within us. And even when the last sun fades away, there may still remain a trace of thought echoing through the void, the echo of a species that dared to dream of infinity. Because in the end, the universe is not a prison. It is the home where we learned what it means to exist. Before you sleep, tell me something in the comments. Where are you listening from? I love knowing how far this voice of science is reaching across the world. If this content made you think about the universe, leave a like now. It helps this channel keep existing. Subscribe to our channel too, and activate the bell so you do not miss the next videos. Here, every week, we travel together through the cosmos, always calmly, deeply, and truthfully. Good night, sweet dreams, and see you in the next video.